Okay, let's start with the notebooks for today. Please go back here to your terminal and execute the git pull. Eventually, let me see. Yeah, probably the best thing is execute checkout dot. So we will recover in the notebooks as in the original state before executing git pull.
I gotta fix something here. I'm sorry.
Okay.
Not share the screen.
Oh.
Just hit share at the bottom.
No. Oh, but it's not here.
Great.
Share screen.
There you go. My fault.
Okay. Yeah.
Sorry about that.
Okay, so let's see. We just did the following. Oh, let's do it complete. I open a terminal here to update the notebooks. So you enter terminal, you go to 2019, and so on, and I ask you to execute this checkout dot. What it does is that when you have played with your notebooks, you have modified them. So if we try to pull the new notebooks, it will say that there are conflicts and you need to figure out how to solve those conflicts. So the best thing will be to execute checkout. I'm sure you are reverting everything to the original state of this. And now execute git pull. And you will bring the new notebooks for today. So today we will be talking about basically three big topics. First, dimensionality reduction. For this afternoon, support vector machines. Yeah, first support vector machines, dimensionality reduction, and we will start a very brief introduction to neural networks and deep learning. I'm playing a little bit with a couple of packages in that area, PyTorch and TensorFlow. Okay, so let's start with this. These topics for today. I'm kind of a little bit more advanced. Yesterday we saw about classifiers, the normal classifier, the traditional ones, the logistic regression, one of them, for example. This one start exploring what you can do in order to separate two sets of instances, or how to create a classifier from a more geometrical perspective. So we will be using exactly the same, the iris dataset, same thing, to get an idea about this. Oh, I forgot to execute something. Okay, so we start with this picture. If we ask a good classifier how it should be, the idea basically, at least for this kind of clean, linear, separable points, is that we should be able to trace a line here somewhere where all the points that we can consider around here will belong to this class, and all the points that we consider around here from this line will belong to this class. Now the question is, which line should we select for this? I can make many lines crossing this area that will do that job. Which one should be preferred over any other? What's the condition, the geometrical condition or mathematical condition that allow us to prefer one over alternatives to that? So let's have a look at this and let's understand the different options here. So here I trace 3 lines. The first one will be, for example, this one, all for the shift. Yeah, the green dots. This is splitting the set, and it will misclassify all those points without any good reason, and it's basically crossing on top of them. Okay. We can have this option, the purple one. Okay, this is splitting the set, and all the points around there, the known points, will be well classified. Not problem about that. But what happens if we have a point around here? Around here, we move on. We got a new flower, and the point for this petal length is around here. Do we have any good reason to think that this is a versicolor? No. Same thing here. Let's say a point here, a little bit high here. It will be classified as blue, but it still doesn't make sense to classify that point being so close to this. So those 2 lines have not good properties from the geometrical point of view. So actually, this one, for example, has a nice property in that sense, that points around here in this side of the venue, or this, imagine this like a highway, and points around here on this highway will be well classified. Points around this side of the street will be correctly classified. So this line, intuitively, it's much better than any of those. So how mathematically we can describe this line as being better? And the clue will be these points here that are marked, that are circled, and those later when we move into the math of this, they are called supporting vectors, and that's why the whole technique is support vector machines. It's basically due to those points that basically declare what should be the good directions to take. Okay. By the way, the idea in general is use a mathematical this. The actual geometrical intuition on this is that any selections that we do here in this point should try to maximize the area of this. So to make this highway as big as possible. That's basically the trick that this kind of score is trying to do. So there are several things with that that makes this a little bit more complicated than usual. Is one, this idea of enlarging this is very sensitive to how you scale those two coordinates. So for example, here, we can have this situation where you have these points spread this way, those points spread this way, and you have this very narrow highway or street. But if you scale them with a certain function, with proper scaling, you get those points nicely, properly distributed, so you can get the street correctly. So a lot of the times, this function, this object, it comes only after a scaling procedure. So all those variables are typically scaled. So that's one thing. Another problem with this, and it's something that we will not try to solve here, is the sensitivity to outliers. So if we consider these kind of points here, that for some reason, someone found that there is a flower that is in this set, but right here, for a weird reason, they will destroy my ability to create a street fulfilling the characteristic. Another is, again, if I have a flower right here, it will kind of artificially narrow my street. So I will not be able to get the right answer. So what typically happens is that, again, not only you scale the coordinates for this, but also you run this after a function that is trying to detect and clean the whole set from outliers. So that complicates even more the stuff. So the detection of outliers, again, is complicated. There are several, and you see that they try to execute different. There are several methods or several models to differentiate outliers, and they work differently for different data sets. But this is an entirely different problem. So SVC, the support vector, SVM, the support vector classificators or support vector machines, are tricky basically for those two reasons. One, outliers. Two, the scaling procedure that you have to execute in advance. Okay, let's move on. And what you can do, at least for the first part, trying to see what you can do when you have points that are too close to others, and or even overlapping sections. So in that case, you have to modify a little bit the equations in what is called a soft margin classification. So we will be creating streets again, to try to maximize those streets, even if we are misclassifying a few elements in the set. So here is a visual example of that. Okay, so right here. So there is a parameter here. C, that control your tolerance to misclassification on those of points in the range. So when this one, the tolerance is low. When this high, the tolerance is high for those values. So what I'm doing all here is manipulating the data basically to show the contrast between those 2 points. So here I am able to, for this set of points, different parameters, that are overlapping, how much I am able to tolerate points being in the other side of the street. So I'm having here this set of points in the other side of this line, and we have those triangles here in this, the wrong side of the street. So like 3 points here, misclassified blue, 4 points here, misclassified green. Instead of this one, where the value is 10, and I have a different number. So we have 3 here, 1, 2, 3 here. So different selection of this will put more or less quantities here, misclassifications. The same trick that we did yesterday when we start moving extra features with the squares, cubes, and we deal about how we regularize all that waves with extra dimensions. We can do here in order to account for nonlinear classifications. So here is the trick. We have 2 sets here, and we are adding the original dimension and the second dimension, and we are putting that as a new feature in the set. And using that trick, we are converting a situation like this, that is very hard to classify, into a situation like this, with this extra dimension where we are able to trace a line, fake line, if you want to get the classification right. So that kind of tricks you can apply to this method. This is another one. This is a different data set that is tricky, because again, the points look very well separated, but we are not able to figure out any line that can separate those points correctly. So here, I am creating what happens a lot in this kind of situations, pipelines. So consider pipelines like small boxes or small functions where data is moving into the first box. The data is changed. You move into the next box, data is changed. Move into the third box, data is changed. So we are adding here the extra features up to an order 3 for the polynomial. So the data enters, and we have first just 1 dimension. After this, we have created 3 extra dimensions. The data moved on. We are applying the scalar here for every one of them. So we are getting nice spread of the data. And after that data is injected into the classifier, in this case, the linear HPC, with these parameters. This is just to preserve the same random numbers. And this is the tolerance that I mentioned before to misclassifications. So we create this pipeline. And this pipeline will behave like a normal, what's the name? Not evaluator. The name escapes me right now. It's exact. We can play with this like a normal classifier, like a direct classifier. So it will have fit, it will have evaluate, it will have the same functions crossing all the pipeline. So we will see here how that works. Probably never execute. So. Oh yeah. So let's see what we are doing here. This one. This one here, we are using it. Here to get the contour of separation. For a linear classifier, using a cubic polynomial expansion in order to get this nice classification. And there are just a couple of points misclassified, 2 or 3 that I see here, but effectively works very well. What else we have here?
The order should do error and try.
What?
The order of the polynomial should try, right? The one that fits our data.
Yeah. So we are creating this here. So the data enters. The first thing is
this number. Don't know it.
We don't know it. We don't know it. So we can evaluate, or we can start using this grid checking, where we are exploring, okay, what happens if we change that parameters from 3 and account for the number of misclassification, the accuracy, the precision that we are getting until we get it right, or until we are satisfied with the result. So yeah, so all those. So here we have 2 big parameters to play with: the degree of the polynomial. This is something that it's out of my hand. I put 3. It could be 4 or 5, I don't know that in advance. And which should be my tolerance to misclassification on the support vector here. So those 2 parameters are something that I need to check out or need to explore with the tools in scikit-learn for exploring different parameters. So yes, what I'm doing here. Okay, this is slightly different. I am inserting the polynomial hidden inside the support vector classifier. So here I was using the linear classifier. So it can only produce a classification, a linear classification, and we are faking the nonlinearity, or we are adding the nonlinear external. But here, in this case, we are using directly this classifier that has an extra argument here that allow me to tell which will be the polynomial that I can use, which degree of polynomial. So we'll basically produce the same or similar result, and the scalar will be here. So here I scale the data, and here I am using the classifier that will receive this name with a polynomial degree 3. Let me see, should get something here. So you can see here, for example, like 2 different solutions in this. So we're using this kernel, using this, where I have my degree of freedom inside the SVC, not having to stack 3 layers in the pipeline, where I am deciding that I would like to use 3 dimensions, or I would like to use 10 dimensions. And there is an extra parameter R that is what it is. What is the R here? The R I don't remember right now. So this is basically the difference between using a polynomial order 3 from a polynomial order 10. Different solution, slightly different solutions. At least for here, for this area, we'll classify very differently. there are some exercises if you want to explore that, and I will keep a few minutes. You don't have to execute a lot of coding here. It's just a little bit of exploration on this. So you can basically take a few minutes and explore this. It's basically copy and paste and play with the solution. You just need to execute this box to blow the boundary. And the question is, what happens if I execute this C high enough, large? You will get something like this. You are not allowing to have any misclassification. So the support vectors will be those three that separates completely the street. Something like this, where you have a small, very small C. So we are having a lot of points here, not misclassified because this is linear separable, so it's behaving nice, but it's putting some points inside the street. So it's putting a few points inside in the danger zone. Yeah. And here I'm using a slightly different kernel that is nonlinear. So I have a new function here that basically controls the curvature of this classification. So now we have a large parameter here. So I am not allowing points to be in the danger zone. The danger zone will be this. And those will be the support vectors, but I allow to bend the space with this kernel that I'm not mentioning. So you can explore exactly the same thing, the same ideas. Just copy and paste and change and play with the gamma and execute here. So it's just executing the boxes. I'm playing with this. I'm playing with this example, but you will do. So all that you have to do is small pieces of code like this. So it's just playing with this. You don't have to code complex stuff here. So just for you to explore here. And remember to execute this function. You will need it to blow the boundary. You have to execute this piece of code. So I will give you a few minutes so you have at least a little bit of opportunity to do something. Yes?
So when you're doing this, in your experience, do you ever have to put intercepts to 0? I mean, does that ever help in these situations? Like if you know the physics or something about the system, do you ever force constants to make it a better fit?
Well,
You don't need to be present. That's imposing a constraint.
yeah, it's
Create a fake data that is on 0, 0, for example, that is the node.
Well, I mean, in statistics, you can put the intercept to 0, but it affects a few other things. But sometimes it gets you a better fit than.
yeah, but we are here we are not constraining. This is not like the linear regression. We are constraining the intercept or something. We are entirely allowing this thing to produce the vector. So the vector, this line is produced from this point, this point, and this point. So this one declares a line. For example, for this case, this one declares a line. So this one declares a line that is parallel to this one. So with those 3 points, you have 2 parallel lines. And right in the middle, you trace the separation line. So there is nothing that I think allow me to force an intercept like a linear regression or something.
What I'm trying to say is that maybe you can add fake points. So, for example, if you want to force the...
Yeah, you can do that, but it's kind of artificial. Yeah. point, and you don't know where to add them actually to force exactly. For example, this crossing that zero here. If you want to cross in here, yeah, you have to put one point like here in order to bend this a little bit. But what's the purpose of that?
So for the purposes of this, you're just better off using the general format and not putting constraints in.
Yeah, but what you want is that all the points that are negative goes into this side. All the points that are positive for sure go into this side, and you want to force that. So probably if you want to do that kind of thing, you will not be using this. You will be using a linear regression or a linear classifier and putting the constraints right there, not in this kind of methodology. So yeah, so play with this is rather simple and it's visually clear what you are doing. What is not so clean is the math that is behind. You can check the video from this professor in Caltech, and you will see that the problem is not trivial. So identifying this line in general is not something that you can do with normal linear operations. You have to rely on some more advanced thing. So I also play with this. If you want to execute this, sometimes I'm asking this one, the linear SVC, or this kernel that allow bending. So you can test both and with the case, change the C to see how many points will go inside, outside. And it's really, really easy, let's say, with a few examples here. By the way, 100 is quite large enough. So when I say infinite, it will be something like 100 or so. Another thing that you can explore if you like. It's changing a little bit this equation. This equation naturally is spreading the points correctly. If you change a little bit these parameters here, you can see that the importance of the scaling. So why you need to pre-scale the data. So right now that is done for you. So the data has a proper spread. Five minutes and we move on to PCA.
might be parking, CV also sign it and something.
Or the beginning again. Can't do that now. Seven. Yeah.
I've tried to do that several times. I can do it for a few days and then because I'm more productive in the evenings when there's no one in the lab.
Yeah.
So that's ridiculous. Like half the evenings is like 2 sessions. That's what you're for. Like 6. Yeah, that's insane. Yeah. Jesus. I just don't like the idea of getting up and stuff by outside.
Okay. Let's move into this one that has a lot of things to mention. Dimensionality reduction. We talked about this a little bit yesterday. When we are dealing with this kind of problems, many problems in science, those kind of things are highly dimensional. And things in high dimensions behave quite differently from our intuition of what our world in 3 dimensions works. So, so when we are in very large dimensions, and you put points on the space, it's most likely that the point, any 2 points that you select will be too far away. So, and you can see that intuitively from just the equation from the Euclidean distance. Every single distance that you add, you are adding 1 square inside the square root, and every one of them will start contributing with the distance. So if you are working with a space with 1,000 dimensions, you have 1,000 elements, positive numbers, adding inside the square root. So distances scale with the dimension. And from the computational point of view, many of those methods scale non-linearly with the number of dimensions. So they try to solve that kind of problems with some tricks, but still. So we should try to reduce dimension as much as possible in this problem. So this, even if we are putting this at this moment in the workshop, is the kind of things that typically happens at the very beginning of a project. So, so basically those 2 things, the clustering and dimensionality reduction is something that is happening at the very beginning. And you don't get any paper published just for saying that you do that, but you do it. And after you start doing, for example, classification, regression, and you play with that, or you want to go into the fancy way and doing it with deep learning machinery, with neural networks, and yes, you solve the problem, and this is so fancy that you get your paper published quickly. So we will talk about this. Actually has a very beautiful geometric intuition behind this, so it's not that complicated. So we solved this one, the first visual intuition of what PCA is. It's probably this figure. It's really nice. You try to select one direction in this slope here in the black line that maximizes the spread of those points. Keep that as the guiding line. So we put this in mathematical terms, saying that the line, the slope that maximizes the variance of those points is the first principal component on this, that direction. And after you do for the next one, you select what is the next direction. In this case, will be the perpendicular to that maximizes the next one and the next one. So very clean from two-dimensional problem. Mathematically it works with this. What we are trying to solve with PCA is basically the singular value decomposition. In mathematical terms, is taking a matrix and separate that matrix or factorize that matrix in 3 terms: an unitary matrix, This is a triangular way, rectangular diagonal matrix, and this one is another unitary matrix. So
Source transpose.
in mathematically, generally, yes, it's a conjugate transpose. So from the most abstract way will be this. So will be transpose and conjugate. But back to the earth into more real numbers, it will be just a transpose, and will be and we replace this star by just the transpose. So visually it will be like this. So we have the matrix, and we convert this matrix into a matrix like this, where the transpose of that matrix, when you multiply, will be the identity. Same thing in this other side. This matrix, you transpose, and you get this, the identity. And this matrix is like blocks with zeros. Okay. So in real terms, we get something like this. So solving this problem here becomes solving this problem. And solving this problem has nothing to do with machine learning. It's just pure linear algebra. So pure linear algebra means that you don't have to rely on scikit-learn for doing this kind of thing. You can do it, I probably never put it here, with SciPy. They have this kind of decomposition inside. So it's not nothing that you have to only use scikit-learn for this kind. So we will see this in a very practical way with the digits, with those handwritten digits. So we have a matrix that is 28 times 28, so a total of 784 pixels. So if we arrange those in a vector, we have 784 dimensions in this problem. So this is our starting point in this. Did I execute this one? Don't forget to execute this one just in case. What? Too big. Okay. Let me see if I can kill some.
Just a question about memory.
Yeah.
That memory here is the memory we are using, or the free memory? That looks like the memory you're using.
This is the memory that we are using. But this is the memory that I am using plus the memory that you are using.
So I can kill it.
There's a lot.
And so yeah, so I will probably kill mine. I will re-enter.
Yeah, how I kill notebooks that are running? They're still running, Is there a way?
Here you can kill this notebook here, shoot down this notebook.
Yeah, but when you see your dashboard, you see all your notebooks and
you see them running.
yeah, so a lot of running. See?
We'll see. Let me see.
On the right side.
Yeah, we'll see.
Running.
Okay, let me see how many. On my Mac, that is not working right. This is something weird with my Mac. I install it from MacPort, and when I kill one, I end up killing several. All the notebooks. So what I have running? Yeah, I have it. But try to kill all this stuff.
Okay.
So now I should be okay.
Yeah, now.
So I start with 90.
Yeah,
I killed that. And, so let's start with this. this has a little bit of memory, not much. It's just this. Actually, I forgot to, I'm doing this here to put this cache equal true. Supposed to improve if the data is already there, but anyway. Sometimes that works, sometimes it doesn't. So this is the idea. We will see this in a moment. We will start with a problem that has 784 dimensions. And we will apply those PCAs in order to reduce the dimensionality of the problem. And you know from the very beginning that this kind of problem should be able to reduce. Why? You have all those digits. Think about all those digits written by hand. It's very unlikely that all the four corners of the digit of this picture contains any information that is useful. So you are pretty much wasting all those corners here, all the corner in this side, all the corner on the left. They don't carry basically any information. I don't think that there is any number that actually is touching those corners. So all of that is probably what we will remove from with the PCA. And there are a lot of things that carry different weights on information. For example, the center for the center is probably very important in this, and we will see that clearly. And as we move radially out, this amount of information will be dissipated. So first, we will shuffle the database, and we will creating something small because I don't want the memory to grow too fast, and that I would like to keep this simple. So I will not be working with the whole data set. I don't need it for this. The first 1,000, and I will be using the last 1,500 for testing. So first, remember that all those pixels go from 0 to 255. So I am rescaling those to get something, a real number between -1 to 1. Doesn't change any fundamental doing that. And I am here visualizing in grayscale the first value that I have in that new database. So remember that this time we shuffle so we don't get the typical same numbers that we get all the time in the previous notebooks. So now, what happened if I ask for two components, the first two components of the PCA? So again, the same idea here. We create a machine, we feed the data, and after we ask questions to that machine to produce. All those things work in object-oriented programming, so this is very natural how they work in that. So we are trying to get those matrices and the representation of them. So I execute this, and I would like to see what they are. Oh, here, what I'm doing here is trying to get exactly the same without using scikit-learn. Just this function here, the single value decomposition from NumPy. So it's just pure linear algebra operations. And I'm here, I'm checking that I actually getting exactly the same values for that. Except for the different methods producing equivalent but not exactly the same results. And you will see here in a minute. So from one side, you get these numbers. From the other side, you get the same vectors but with a -1 factor on top. So they are equivalent, but they have a different factor, a different direction for that vector. So we have just 2 dimensions in this problem. So we can compute what is the inverse of that. And we see that the values are not the same. So the value, when we invert this thing, we are losing something. So that's the whole purpose, right? We don't want to lose much, but we are actually losing a lot. And of course, with just 2 vectors, it could be quite a lot. So here is the idea. So we compute how much is the difference in those vectors in average, and is this one, right? Let's see how that looks like when we convert this. So this is the visual representation of having this original number converted into a vector of 768 components, computing for my training set or my points, the PCA, taking just 2 vectors that will be combinations of those original pixels, and using that to convert those back into a figure, into the original pixels, into the original dimensions, and what we get. So we get something that resembles, but with a lot of visual problems. Again, another thing that you can see, well, this is again clear, that all the main components are concentrating all the information in the center, but it's hard to see from such a small conversion. So we can do the entire opposite. Instead of having just 2 principal components, I will get all the principal components. So it will be just a change of base, basically, an entire transformation. And this is not the digits convert. These are just the values of the principal component, one of them. I don't remember which one. So it's not actually the number. It's not the conversion back. It's just the value that we'll have in this, again, 768 dimensions, because we are keeping all of them. So they will be transformed, but they will be exactly 768. I will arrange those again as 28 times 28, and I put that vector back. So no resemblance, but they contain exactly the same information. So this is exactly the same as this, just in a different base. We can convert back. I think that, okay, no, before that, just to have a look at how that looks for a very high vector in this principal component. So they have 768. I am looking at the next, the 100, 101, very high. So they are basically noise. They are very noisy. They don't get any idea. So you see that those look more compact. Those are very noisy. They don't carry much information. So the idea, the question is how many is good enough, and how we measure what is good enough, how many principal components we should have. There is this function here for the PCA that allow you to say, okay, for each individual element, how much they account for the variance in the data. Remember, the first one here, when you see this one, this component here, this first vector, carries most of the variance. The second vector, there are not just two vectors here, it will be this perpendicular here. It carries the remainder of the variance in the data, right? So let's go back here. This plot will tell me exactly that. The first vector here carries most of the variance, and the variance of the data goes quickly diluting for the next and the next and the next vector. So you see all those vectors here, from the vector, probably even from the vector number 100 to the vector number 768, the amount of variance that they carry is very little. So we can probably get rid of them. But let's formalize how we can measure which is a good point. So we can decide how much variance I am able to tolerate to keep in my subset. And let's say that I would like to keep just 90. So all that I have to do is accumulate for the first vector, count the variance, and sum the variance for the next one, for the next one, for the next one, for the next one, until I reach 90% of the whole variance. And this is the point where I will be satisfied. So I declare what is the variance that I would like to keep, 95, okay, 95 or 90%. We are just taking here 90. So we are using this NumPy operation to sum the vectors, accumulate the values for this explained variance, for this equation. So it's basically this same curve, but we are accumulating the values for the next and the next. So it will look like this, right? And we are dividing. Oh yeah, we are dividing by the by total. Okay. Yes. So you get a curve like this, and we will satisfy here. We can identify which point is that. So this is just the plot. Where am I getting this? Oh, here. So I am trying to get what is the point here? What is the point where this is going always up? So this sum. Let me see. Let's do this. I should have done this. Let's split this. So I get this. Let's have a look at this. So here I have 9%. If I include two vectors, I will have in 16. If I include 3, I will have 22% of variance. If I include this, I will jump into 28, 33%, 37. What I here around here will be 51%. Around here, I will get in 60%, 62, 63. Around here, I will have 80% of my variance if I collect vectors up to this point. And the whole thing will stop for me because I declared 90% around here. I reach this point and I will be happy. I decide I will be happy with 90%. So it's basically counting which index is this point. The way for doing that is getting this as this. At which point this is smaller than 0.9. So all those points. And you can sum this, and truths will be just like ones. False will be like zeros. So if I sum this array with NumPy. I will get exactly 80. So that is where the 80 comes from. So with 80 vectors in this set, I will collect 90% of my variance. Just 80 vectors. So it will be 80 vectors out of 700. So the reduction is quite important. So here. And this time, with that knowledge, with that fix of numbers, I will be able to create a new PCA where I just fix in 80. I am keeping 80. Why? Because I would like to execute the same trick that I did at the very beginning for 2. It will be getting the original. This will be the original number. And this will be the number, get it from the vectors in the PCA and convert it back into the pixels. So you will get this figure, right? So again, you can see that this one effectively resembles a lot to the original one. For all of them, they collect the information about it. That this is a very intuitive, very geometrical way of approaching the PCA. What is the meaning of that? So this is, again, recapitulating here, this is what you often do in machine learning. You receive the data. Hopefully you don't have to clean that mess. So somebody else is hired for that. He will be the data miner. I receive the data clean, and I'm satisfied with that. First thing is to inspect what the data can tell me. Clustering, so I can not look at the results. Imagine that they have the, for the classification problem, they have the results. I will not use them. I will just see the data if there are similarities. So if I receive the data for all the statistics of all the countries in the world, let's see if there are countries that are similar somehow. So that will start giving me ideas about what I can do with them. Another thing is to look into this. I get all those variables. Again, this looks very, let's say, clean when you deal with this kind of problems. The classical problems for machine learning, images, on the risk for giving loans, mortgages, and things like that. It's clean. In science, we have a step in the middle that is hard. For example, we have molecules. Imagine that we have molecules. So, and we will be doing something like this. The position of the molecule means nothing. Just a number. Let's say the positions of a molecule in a space mean nothing to deliver into this. Why? Because you rotate the molecule, and the molecule is the same, but all those numbers have been changed. So positions of in let's say in the Euclidean space in the space, they don't relate to anything that any procedure can do with this. For example, if you are injecting this, and we will see this in a minute, into neural networks, you should not be using the positions of the atoms in the space to try to manipulate and get, for example, the energies, absorption energies of molecules or things like that. You cannot do that. What you can do is to create features, and that's what people have done, and people specialize and even work on entire thesis trying to figure it out. What you can try to get from a molecule, from a data structure that preserves, that produces the same values, no matter that you rotate the molecule. So what operations you can do in order to get a set of vectors that's called feature engineering, which are the features that you can extract from this in science, that are vectors, that are a complex structure. And so the data is not so clean. So you have to do something around that. And also in physics, when some of those things come from simulations, so you cannot trust that these people trust that the number is like that or the values of energies are like that. There are possibilities of having values that were bad simulations happening in the middle, numbers going wrong. So you will see them as outliers. So structures that have energies that this doesn't match with the similar structures and things like that. So you will be doing that. But when you have the features, you can start playing with this, reducing those. They will start reducing, for example, by symmetry. The symmetry will reduce those operations. This is a lot of the things that this kind of things are doing in the middle. And after you move into classifiers, you move into regressions. If you want to predict energies, if you want to predict if something is a good thermoelectric or is a good candidate for lithium batteries or things like that. And we saw yesterday a couple of examples of that, linear regression, so regression problems and classification problems. So now we will move into the fancy things, that is neural networks. And we will probably have, some time to play with them a little bit. So let's see. Let me see if I can close this one to save memory.
I closed a bunch of stuff so you shares.
Okay. I just killed the kernel for this one. Okay. So I will offer a very, very soft landing introduction to neural networks and deep learning. I'm not by any means an expert in in neural networks. It's not my field of research. It's something that I use a lot of the time like a black box, but I have some idea. So I will transfer that idea to you, basically. These topics are complicated. I am basically offering you this, following this this material for a guy in Pittsburgh, the Pittsburgh Supercomputer Center. From time to time we have, and if you are interested on that, please tell me. We offer, or we receive offers from hosting here, like video conferences for big data and parallel computing, OpenMP, that sort of things. And during the big data one, there is a section on neural networks with TensorFlow. So I am basically basing using that as the guideline for the delivery for you. But if you are interested on this, tell me, and we can arrange hosting that big data workshop here in campus, so you can see the video and you will receive accounts and you can start playing with Spark for data mining, and there is one section on neural networks, so you will see a little bit of this very similar. So I'm basing this from this lecture. Yes.
I don't have that one.
You don't have what?
That no.
You have to.
And I did do the git pull and it still doesn't.
It's not. You don't have it. Let me see. Maybe I didn't pull it.
I did just do in the 2019 data hands-on. I
Yes.
did git pull and nothing.
And you get that there is nothing new.
And it doesn't. The last thing that it tries to do is the dimensionality reduction.
Let me see.
You do git checkout dot.
Yeah. Let me see. I will check. Okay. I will check GitHub to see that it's okay. So GitHub.
I think that's
home. HPC.
Yeah, I have it now.
It's now.
I have it. Now I have it. I need
Okay.
you to like it, check out.
Ah, okay.
Thank you.
Yeah, should be there. Okay. Neural networks. Neural networks is actually an old idea. And they come from two sources, basically. The idea of mimic nature and how nature solves problems, in particular how nature works with biological neural networks. And the other idea will be the idea of perceptrons, more from the machine learning perspective. So basically, and again, I'm not a neurologist or expert on the brain or anything like that. So a neuron is something like this. This cell receives some impulses from some other neurons. They, based on those impulses and a function, they decide, they carry some impulses to some other neurons. And they cascade that operation over and over. And that's how people think brains work. So different cells that transfer electrical impulses one to another. And if they receive, one neuron receive sufficient input, it will transfer that input to the next one. So that is translated into computing, like some values entering into an input, that input being weighted by a value here, those values collected from the different neurons, from the different inputs here, being collected here. So we got the sum. That sum passed through a function that is called an activation function. And based on that, it produces an output. And that output goes into as an input for the next neuron and the next neuron and the next one. So they move in cascade. That's the biological origin, or that's the biological metaphor for use into this scheme of neural networks. The other is the idea of perceptron. A perceptron is something similar like this, for example, for a linear classification or something like this, very similar to what we did this morning for support vector machines. We are trying to figure it out. We have a value here, a weight, and we have another value here, and a weight. And we enter those into this machine, and we get an output. And we check the output if it matches with the known value for that classification. If not, we should have to change this weight in order next time to get the right answer. So changing will be the next problem. But this is basically the idea. If you have something like this, two inputs, one output, and we change that, just that, you get this idea of perceptron. And this is probably from the 50s. It's one of the, let's say, grandfathers of neural networks. Just two inputs, one output, and you change the weights just to accommodate the next input and give it right. So if you do that, you will get something like this, some planes, where you separate right from the two instances, the two classes here. Okay, so again, you can play with this, and you can have several inputs here. This neuron will collect all of them, and you will have an output. And you can cascade this into new layers, what is called a layer of a neural net. This one, for example, is a neural network with one hidden layer. It receives the inputs here. It moves into this layer. It collects the values. This is what is called a dense network here on this side. So we are basically connecting everything with everything here. So there are, if we have n inputs here, we have n weights here just for this neuron. We will have n weights here for this neuron, all of them. And we have n neurons here in this hidden layer. So the total number of weights will be n times n. You will see that, how that goes. And now we have all those propagating the output to all this output layer. So you see this one, you see this one, you don't see this one. That's what is called hidden layer. You don't control this one directly. So this is what is called a non-deep neural network, just a hidden, just one hidden layer. If you don't have any hidden layer, you have a perceptor. You have a linear operation. When you have multiple layers like this, 3, 4, and hundreds, we are in what is called deep neural network. So among the hidden layers is much, much bigger than the amount that those input layer and output layer. Each one of those has n times n weights. Apart from the weights, they can, and we will see that later, there is another number that is a bias that change the numbers. So those accumulate quite an amount of numbers. And there are, I forgot to put this, a plot. So you can, one way of counting the complexity of those numbers of a neural network is how many weights that have. And some of those neural networks for companies, for complex procedures, could have several millions of weights to play with. So how that complex that could be. Of course, the complexity means that computing this is a function not only of how big it is, how fast this network is, but also the number of layers that you are including in this. And we will see in a minute that things can go far more complicated than that. So a very relatively simple, what is called a feed-forward network will look like this. We have an input, we have a first layer, first hidden layer, next hidden layer, next hidden layer, and after the output, right? In a classification problem, what you will do, for example, if you are classifying the 10 digits, we will have 10 neurons here. And all those will give me the probability of the number from the input, or the figure image from the input, to correspond to being 1 or being 3 or being 9. But also the input and the output could be an image here and an image here. So you could have hundreds of pixels here, and the output could also have hundreds of thousands of pixels at the others. Okay, so this is the traditional architecture, or the simple architecture for that. For one neural network with 15 neurons here in the hidden layer, one hidden layer. For example, thinking about these digits. So you will have a vector here, one for each pixel. Each pixel in the image of those for the digits, we will have 784 here. we will decide how many we will have here. And we produce here 10 outputs. And based on them, we will decide that then the neural will output what is the probability for something being a given digit. Those things can be far more complicated than that, and I will show you this figure that I found on internet, where they have the whole classification of good classification of complex neural networks. So I will just move into this first line just to get an idea of this. So this one, very simple. 2 inputs, 1 output, right? It's called a perceptron. So the precursors of a neural network. A perceptron is only able to see, to serve as like a linear classifier. Cannot do better than that. So you will have an equation that is A times W1 or X1 times W1 plus X2 W2 equal to a function here, and you want to play with the weights. So basically twisting and a slope and intercept in order to make a classification. So you can see that this is purely linear. And this one, we have here 2 inputs, a hidden layer, a densely connected, so everything is connected with everything here, and the network is moving just in one direction. So this input goes into this one goes into this one. So this is a feed-forward neural network. I don't see the difference with it. So here we have inputs, 1 layer densely connected to the input, 2nd layer densely connected to the first hidden layer, and after an output with 1. So this is the prototype of a hidden layer that we will be using for the first examples here. And you can also see this kind of neural networks. You see these points, meaning the output of that neuron goes back into input for itself. So that's why it's collecting those loops here. They have some other versions where they keep previous values, the output, but those are dissipating with that. So with every new cycle, the old values have been discarded. So they go on, and I will not go into more details than that. There are some that are used for images, that we will use exactly one of those for the example down, are called convolutions neurons. So they're very popular for that. I don't see them much of a use, at least on my area. Or all that, what I see, for example, people predicting properties of materials or things like that, is just using a lot of, or quite a number of hidden layers, 3, 4, 5, but not anything like this. So those are probably for people working with images, things like that. So the whole zoo of neural networks. So let's go back here. And now let's concentrate. You got the idea of an input receiving a weight, all those inputs times weight being collected here in a sum, and that sum entered here into an activation function. Which kind of functions are served as activation functions? Well, there are quite a few. Here, I found this figure basically collecting many of them. So here you have the equation, and here you have the derivative. Some of them are continuous, some of them are not continuous, or continuous but not having a derivative that is continuous there. So the most popular are something like this, that is basically like the logistic regression. So just something that smoothly moves from 0 to 1. There are several ways of producing a curve like works like this. Tangent, parabolic tangent is one of them. So they are mathematically slightly different, but they follow basically the same idea. So all those are mathematically different, but they have the same. So they differentiate in the slope here, in the how the derivatives change in the asymptotic behavior. And this one is often used in deep neural networks, this rectified linear. So it goes from 0 into a constant slope when it passes a threshold that you can later move. And there is a version of this one that is continuous. There is this one, the soft blues. So the most popular are this one, and some version of this one, the logistic or arctank or whatever. Those are that are often used. I'm not really sure why some people would choose one over another. That escapes me, right? So sigmoids is this one that I told you. Sigmoid, any version of a sigmoid. The rectified linear or the soft blues. Those are used functions that you inject here. So those functions operate over the sum, plus eventually a bias. The bias will just simply shift the whole sum rigidly. And you use that function to declare how much you will propagate to the next neuron in the network. So now with all that information I will do one exercise, follow entirely one neural network like this, step by step, to get a clear idea what we are doing. So imagine that we have this neural network. We prepare this machine like this. 3 inputs, 1 hidden layer, densely connected, and finally 2 outputs, densely connected. So dense connection here, and they move forward. So now, typically the first step is, after you create the network, is associate values to the weights. So this neuron has 3 weights here. This neuron has 3 weights here, and this one has 3 weights. Those 3 weights, I decide at the very beginning that I would like to use these 3 values. Typically, they are chosen randomly from a certain distribution. You don't control that at the very, select that, and the neural network will operate them and will change them, and we will see how that happens. So again, second hidden layer, second hidden neuron will receive those weights, and this will receive some weights. And when time comes to operate with this layer, we will use these weights here and these weights here. Okay. First step in this process, the inputs go and operate over the hidden layer. So what happens is they will receive the inputs, this 0.5, entering here with the first weight, plus the second input times the second weight, third input times third weight. We get this sum, we pass it to a sigmoid, because we will decide that we will use it for all those, we will be using sigmoids, something like this one, the logistic one. This is what I will be using. So we got this, and now this neural network has these three values here in the middle. So that's the content of the hidden layer. So now, next thing is propagate this one as inputs moving to the output. And so again, this one will have three weights. So we will be using those numbers here, down here. This one has three weights. We will be using the numbers down here, right? Same thing. So first input from the first hidden neuron will enter with the weight times plus second hidden neuron times second weight and third one. And we collect that, we sum, and we produce a sigmoid. We operate on over a sigmoid, and we get this value, right? Same thing here. And we end up with this value here for this. Now, we evaluate this if this is something that matches the training, the output for the training set. If not, we will see, the problem will be to change all these numbers in order next time to get it right. This is the challenging thing of this. So operating with the neural network is piece of cake. I can teach my son and can do it. It's not a big deal. Changing this is the tricky part of a neural network. I am doing exactly the same here. Instead of doing algebraically, I will be doing like a linear algebra problem. It's exactly the same. So I will put these numbers here, those numbers of these three neurons and the three weights here as a matrix. So this is my hidden matrix of weights, right? It's exactly the same. It looks like a matrix, just that. So the input will be now, instead of the three numbers here, I will operate with it as a vector, right? So this operation here, before the sigmoid, this operation here inside is exactly the same as a vector multiplication. In NumPy, it will be like this. So the matrix and the vector, and we get this array. It's exactly the same as we have right here. So the values inside here. And now we can operate in NumPy with a sigmoid over all the elements, element-wise. And the function for that is this one. So I took it from SciPy, a sigmoid, and I operating with that sigmoid over the array of vectors. I am getting these values here. So these values here are the values that actually, those are truncated, but are the values that you see here. This one, and this one. So now we will operate again with the weights here. So this one, these weights will become a matrix, this time 2 rows, 3 columns array. This one here. We operate with that one, and we will produce this solution here. Yes. Wait. No, sorry. This is the output, and now I am computing the vector here first. So now I got the elements here, those elements, and I compute the sigmoid on top of that, and I will get this. with the sigmoid on top, and I will get these values. If I change the weights, I will change the output. The tricky part is how to change those weights in order to get the right output. We'll see that. And I forgot. You can, so you can put the same thing. So you can, all those things that I did in step by step is exactly the same as doing this operation here in one line. So I am executing the sigmoid. So this time you can see the function operating like in reverse. This is the sigmoid for the output, operating on the dot product of the outputs that I got over the sigmoid that I produced from the inputs and the matrix from the hidden layer right here. So you operate this and you get exactly the same result. The message from this is that we are converted a neural network into a linear algebra problem. And that's the reason why, well, first, linear algebra got like a revival in high-performance computing. It used to be the most important thing in high-performance computing. That's why we have BLAST, LAPACK, all the stuff. But now we can compute all those things entirely inside a GPU. And there is another interesting thing, is that it's linear algebra and it's only linear algebra. And that's extremely important for a GPU. Because for a GPU, you don't want to, it's extremely expensive to move the data in and out the GPU. So with this, you can operate the whole machinery inside the GPU and only at the end take the results back if you want to see them. So this fits very beautiful into the way as GPUs work, and that's why they are so often used for this kind of approach. So now, there is something else that I can do with this neural network, and it's right here in this figure. I can take the sum of the weights and the inputs, and I can rigidly move that. So it means that I can operate with the sigmoid. What are my sigmoids? So with this B, I can move a value that ends up being here. I can move it to this point. At this moment, this neuron will be activated. If the value remains here, the neuron is deactivated. They will not produce output at the other side. And that's one of the reasons why people use this one, is because if you create those with random values at the very beginning for the weights, in average, half of the neurons are activated, half of the neurons will be deactivated. So that's pretty much what people use is this kind of a structure. But computing the derivative is tricky. That's the downside of that. And we will need the derivative function. So those are called bytes. So they add more values that we should be adding to the problem. Yes?
So, sorry, say again about this GPU. So if you put on inline everything. So
no, it's not. No, here I'm doing linear algebra on the CPU. Nothing is happening in the GPU with this.
So
The point is, two things. GPUs were created originally for games, so that's where they come from. So for graphics processing. Graphics processing means what? Means that if you are in those games, shooters, let's say, typical games when I was young, all that you have to compute are the positions of the objects, and if I rotate, all those are rotation operations. So everything is just rotation, translations, All those things is linear algebra, pure linear algebra, with not extremely complex elements, so just too many of them. So every single cube around, every single particle of dust needs to be rotated, or you need to operate with it. And after they have to apply textures, and they have to apply lights, and they compute transmission. So all those things, you can recast them as a lot of linear algebra or vector operations. So at some point, people realize that all those things can be used for more useful purposes, not for games, but for processing data, if you can put the problems in that realm of linear algebra. But there is a problem with that. GPUs have a lot of CUDA cores, what the people in NVIDIA call, but those are not like CPUs. And it's extremely misleading, and they take advantage of that, saying that this CUDA, this graphic card has 4,000 CUDA cores. And they have 4,000 CUDA cores, but my CPU I have is 4 cores. Oh, they should be amazing. The reality is that those CUDA cores is not something equivalent. So we are not putting apples with that. One thing, they are able to perform operations, yes, but the movements of memory and how they work have different time scales. One. Second is moving data in and out of the GPU is extremely constrained. Even if you are using those cards that are implanted into the main board, those perform much better than those that are just PCI Express. Those, let's say, that you buy for $1,000 for your workstation. So there are some others that are far more expensive, but it's still, moving data in and out is expensive. So if you are doing something like the kind of things that I do in my area, you need to move data in and out all the time, because you are computing DFT, you will need to take the data, computing for different key points, doing some stuff that will complicate things. So GPUs typically do not perform that well. They perform very well in 2 scenarios typically. Classical molecular dynamics for people in those areas, where they are basically moving particles with some force fields. So all those things fits natural in that environment. And you don't need to observe the environment. You can throw those atoms there, move them, and get the result. And after a few femtoseconds, and if you want to do something with that, after that, it's okay. But you can leave the box running there without observing the box, without taking the data back, the memory back. Or these kind of things, neural networks, where again, you can create those machines, play with the numbers over and over and over, use the entire data set and get the result, change the weights, do it again, change. So they fit naturally in that environment. That is why they are so successful into that thing. But no, what I'm doing here is purely CPU. But I could have, and this is exactly what is the PyTorch or TensorFlow are doing, is doing linear algebra. Those are packets for linear algebra happening on the GPU. That's the advantage of those packets. And we will see, for example, with PyTorch, that this is everything that you can do with the linear algebra, they can do it exactly the same, very similar to NumPy, but you can do it on a GPU. Clean. Okay, so let's continue. Biases. So another extra variable that we can play with, the bias, and that basically change the activation, the condition of the neuron being activated, or changing the how much it will be activated. So another thing, another perspective. Just the linear algebra operation, so just the weights are basically responsible for scaling the problem. It's like a matrix operates. So it's just basically scaling and doing rotation. This is what the neural network do with those weights. This is the linear algebra. The bias is just providing translation. So you are moving the data into the activation or the deactivation side. And those activation functions that are non-linear, you see those, the sigmoids, are basically responsible for the twisting of the values. So, and again, the recursively layer by layer operation and all, and some of that reinjecting are responsible for twisting even more the data. So you can basically get whatever you want out of that. Okay. So let's go into the hard part. I will not be dealing with the math. It's just for you to know that this is the hard part of this. And I mentioned already this, is once you have this and you have this 3.5, 8.5, what happens if the value that I would like to see is, let's say, A here, 0.8 here, 0.2 here. And they don't have to normalize to something, but I want a different value. What I have to do to get a different value? Well, yeah, the answer is, for that question is trivial. I have to change this. And if I have bias, I have to change the bias eventually. Yes. The problem is how to change those things. Any random change will not help you much. So that is what it calls the backpropagation problem in neural networks. And that's why for a long time, people only reach up to a very simple networks because they have to do this backpropagation by hand. So you cannot go too far doing that kind of stuff. The trick with the deep learning is devising algorithms so to predict those backpropagations without explicitly computing the derivatives. So what is we have? We have this function here, the output of the neuron here. That is a function of all those bias, all those weights here, and all those weights here, and all the weights that you can consider over as many layers you have your neuron. So the best that you can do is to follow the things backward. So compute this derivatives, these partial derivatives, and start following this. What is the change that I'm doing here from this one to this one, and this one? And after going from those changes into the changes that I have to that I apply into get this one, and this one. When you move all those derivatives back, you know what this should be the values in order to get all this in the right path. Hard problem, typically only possible if those activation functions are very well behaved, such well behaved that you know the derivative of them, so you can compute the derivatives cleanly and go back. Otherwise, you have to rely on something else. Again, I will not enter in that. I just referred as the original document to this blog and especially to this video. They are really good. They show you very graphically with animation of what it means to backpropagate it. So they are very didactic in that. So I will not mention that before that. This is the hard part of neural networks. This is something that TensorFlow is doing for you when you prepare the network and you do all the machine learning. So if you are not planning to develop your own neural network package, it's good to understand it, but you don't need to understand it that well. So, we are basically here solving a gradient problem, well, a derivative. The trick for that is using basically the gradient descent. So the algorithm that we mentioned several times before when we were doing regression, I think, we mentioned this. And there are several of them. There are several ways of thinking about that. One, you require the whole points to produce to compute the gradient and follow the gradient until we reach the minimum. There are improvements on that when you are using just one. But if you remember yesterday that you saw that when you use just one, you start jumping a little bit crazy in the surface. Or you select batches of input from your training set to compute an approximation of the gradient, and you move into that gradient, and next time you select a different batch of points. So imagine that you have 1,000 points and you plan to work with just 100. You select randomly 100 points. You use those to compute the gradient. You move towards the negative of the gradient. You move towards the minimum. And you get a new different set of 100 points to compute the next gradient and follow. So it will wiggle a little bit, but it will be much better than having to deal with the whole data set, with the whole training set. And they add some other things like preconditioning ideas. So one is that you can control this jump adaptively. Another one is that you can add some momentum, some inertia. So they will follow, they remember a little bit of the past, and they don't go in stridely changing abruptly from this direction to the next direction. So it will change gradually and follow a more smooth curve. So all those things are inserted into those algorithms for computing the gradients. What you are doing is basically doing these operations, changing the values. And this is called, when you do that, this is called an epoch. When you do with the new set, you get a new epoch, and you change until those values converge. For some of those things, you can guarantee mathematically the convergence. There are some of those crazy things here that nobody knows how those things will work. So there is no way to, nobody knows how mathematically, let's say, provide strong arguments for convergence of those crazy stuff. Okay, so that's what they are doing. And so I have here one example, right? First example, this looks ugly because I will be using purely directly TensorFlow. So you get an idea how those things work with TensorFlow. I need something. This will fail except if I install something here. Let me see. I just realized this morning that I need one extra package. Let me see. If I execute this, oh, we don't have TensorFlow yet. Okay, first we need TensorFlow.
You said it's ugly because what? Why it's not ugly?
Imagine these kind of things. Can you? Let's say it will be. I imagine it would be. This kind of, even these neurons that have recursive inputs here, trying to figure out if you can come out with if changing the weights will send you into a minimum.
No, I just said the code is ugly.
The code is ugly, yes, because there are much easier way to build those those neural networks without having explicitly built one layer and the connections and the next layer the connections. There are much easier ways of doing this. But so I will install this Conda search TensorFlow.
C.
What?
Don't forget the C.
Oh, yes, yes. Sudo. You know what the minus C does?
All the variable. As the environment variables down to show.
Okay. So I will install this one. So for this one, we will need this TensorFlow, and for some reason, there is one package that I need here just to get the data. I will collect the name of it. So let's see what we have here. So I will declare, okay, I will load TensorFlow here, and I will collect in the data from the MNIST, so all those digits. The same. So I collect the data, I will store that in someplace, the TMP. So I will be creating something with 4 hidden layers with 500 neurons each. And I think I will densely connect all of them. So the input will be 768 values, the values for each pixel. They go densely connected into 500 neurons in the first hidden layer. They will be densely connected into 500 neurons in the next hidden layer, third hidden layer, fourth hidden layer. So quite complex structure, but they're still very feed forward. So the first layer computes the next layer computes the next one. They are not going backwards. They are not fancy stuff. And I have 10 classes, so at the end I have 10 outputs that I will like to classify. And I will be using batches of 100. So that's what I'm planning to do. Whoa. What the hell is this? Okay. Let's see. Okay. The only thing is, okay, it's working. Done. Because I prepared this with a different version of TensorFlow. I was wondering if we will get into troubles. Okay, so it's working. Forget about the errors here. There are probably. So the point is, I was using this when I installed here was TensorFlow 1.10, and don't understand why it's 1.10. I have 1.14 here, so I was concerned about the version of discrepancies on the API. So we have this 500, 4 layers, 4 hidden layers, and 10 outputs here. I will be training this in batches of 100. So here is how I create them all. This is exactly the equivalent of what we do with the linear regression, the k-means, everything. When you prepare the machine, no computation is happening here. It's just creating a function, basically. So I have the first hidden layer. I am declaring the weights. So this is a Python dictionary where the weights are a normal random distribution of 784. Remember that we have 784 because in that case, we have 744 elements here. So if they are densely connected here, we have 764 entries here and 764 weights in that collection. So that's why we have that value there. And also we have biases on all of them. How many biases? As many as the number of nodes and neurons in that layer. So I hope that this first layer is clean, right? And same thing for this one. I'm just changing the values here, how they are connected. But again, I'm creating random numbers with a normal distribution for all the layers here. And here I have my output layer where it is receiving the values from the hidden layer here. And again, I have a bias at the very end of this layer for producing the output. So here I'm declaring the topology of the network. So I am here adding this with the hidden layer. So the input data with the hidden layer and the weights and the biases, and goes here with this activation function. This one that is 0 up to a point, and after it goes constant, right? So in average, half of those will be deactivated at the very beginning. You will not put data into the next one. Same thing here. I will be using this same activation function for this layer, and this layer. Nothing outstanding here. And the only thing is that I need to connect this correctly. So this one is connecting the output, the input is connecting to this one. Here I'm connecting this one into the next layer as inputs for the next layer. Here I'm connecting the L3 here into the layer. And here I'm connecting, I did a mistake. I actually wasting one layer here. I'm connected wrong. So you see, this one should connect the L3, not the L2. So I'm creating one, and though I'm wasting all those outputs and going nowhere. So this L3 is wasted. I did it wrong. So here I having the output with the weights and getting the output. So this is this is the mathematical description of how those matrix multiplications and vectors are happening in the sequence. So so here is the matrix multiplication and translation. here is the activation function after that. So linear algebra in a different way of presenting it, but linear algebra nevertheless. And here is the function when I'm using this model here to actually train the data. I will declare it that I would like to pass 5 times of the old data. So here, for all those epochs, I will be taking a batch, a portion of the data, and I will be training, I will be selecting the numbers that I will use for training. So here is the evaluation happening here. And what you see here is that they are telling me the loss here that I'm getting, and I'm just executing 5 epochs just to make it quickly. And I'm getting this accuracy in that. It's not that bad, not that bad. It's similar to what we did yesterday for the other classifiers. But it's basically because first I did a mistake with how I put that layer, and secondly I'm using just 5 epochs in this set, and I'm using a very restrictive number of elements in this. So several things I did in order to cut the size of the problem that are affecting my accuracy at the very end here. Right. I will not enter in too much details into this. First, because I'm not expert in this, I don't want to embarrass myself with this, which is often used for people in images, processing images. And those are convolution networks. They use some idea that it comes from math, from mathematics, about what a convolution is, but the way they operate with those in terms of matrices is slightly different. It's a pragmatic way of thinking about a convolution. So it's not the same thing that in physics or mathematics we think about it. So the idea is basically that if you want this digit could probably be equally well represented if we translate that a little bit one way from another. So you translate the whole digit a little bit, it's basically the same. So we should be able to capture that translation independence out of the image. So what they are doing is carrying the size of the image to a slightly smaller size and consider all the different translations that you can produce here for getting a matrix 24-24. So you can start from here, for example, and you get the matrix like this. But also you can move a little bit here and forget about 1 pixel here, and you get another one. You move another, you get another image, and you collect that information here. So you have a number of channels here that are representing just 24 images. And after you start operating with those, what is called a convolution, that is basically you have those matrices. Remember that originally we took this and we converted it into a vector, a long vector. So we are losing entirely the geometry of this. We are not adding any information about why this pixel is close to this pixel nearby. The connectivity is lost. This is trying to carry that. It's just an operation of the matrix, the pixels that you have here, with some weights also in a matrix. And you are overlapping them and you're summing them as a matrix. And you get some of those channels, and those are called convolutions. And they go later on here, deep into the neural network, into traditional networks with weights, and they go back into the output. So they include far more complicated stuff. It's basically this, that I only see application for images because they have that. Yeah.
Are they taking into consideration any like which side you cut, or they just cut it?
Yeah, if you cut it smaller here, you get more images, right?
Well, I meant like if you're looking at an image, do they?
Yeah. Some of them, for example, are trying to capture different people on the image. Where the people is, which people they are referring to. And so that is another thing, that the output could be several people. If you are using this for an image face recognition thing, you have an image and several people could appear in the image. So at the end, you will have, okay, I recognize this with this probability, but also this one could have a very high probability on a different location of the image.
So you might split them into two.
Yeah, you can have multi-label outputs in this thing. So the probability of this person being in this corner of the image is this for this set of people, and this probability for another person in the same image with some other probability. So those things can be complicated. Another thing is that you can use all those things again to not get something like this, a categorical output, but an entire image at the other side of the plane. So there is a very cool example where they have, for example, they capture the image from a photo, and they change the picture and texture and colors based on a different photo. So you get the same content here with a different style. This is content and style. You search for that, you will see the cool images that they produce that. Or take a photo and producing an image that resembles the style of Leonardo da Vinci, or an impressionist, or Renoir. So they take the image and they train those neural networks to produce an image that capture the style of somebody, a painter. So yeah, the output could also be an image. So yeah, those things. So I am just using this excuse to show a similar operation. This time I did it step by step, but this time I will be using convolutions. So same stuff. So if this is okay, I have the data here. So fast. Okay. So here I'm creating those things. I'm trying to follow this. So the image is 28 times 28. I am entering these convolutions where I'm truncated to 5 times 5, I'm not wrong. Again, this scares me for a lot. Second layer here. So those are just they capture the variables, so where I would use it here. Let me see. Here, this is the function that I'm using for the activation. All of them are this linear. And here, I'm producing the output with 10 digits. So 2 layers here, 1 normal layer, traditional here, and the output layer. So not big computation is happening here. This one, so here I'm creating this network, measuring the accuracy and doing batches again of 50, which should be doing 100. And what I'm controlling, I'm losing something here. The number of epochs that I will be doing. Oh yeah, I don't want to do this. I will be doing something like this. Otherwise, it's super expensive. So this thing, if I had a GPU That is not the case right now. I could execute this much faster, but I don't have that, so I have to constrain a little bit this.
When you have a GPU, like
On this virtual machine, no.
No, I know. When you have one,
You can declare. It's exactly the same code.
But then we install different.
You have a device. You get a device that it will be the GPU, and this operation will happen on the device.
Yeah, but I saw when you're installing the TensorFlow, there is a GPU.
Yeah, they have the GPU, but I don't have the physical
so
GPU.
You need to install another.
Yeah, you have to install a different package.
But the commands are the same.
The commands are the same. The procedure is the same. It's just the device that changes. That's the idea. So you guys, you see that you start with something really bad here. Each epoch, I did it very short, so I stopped this quickly. But you see that even with that, I got an improvement on the accuracy using those convolutions. So I think with this one, you can get, what is that side? There is one side that they are capturing the performance of many different techniques for predicting those numbers. This is a classical problem. And I think with neural networks, they achieve 99% with some of those convolutional neural networks. They practically get all of them right. So this is this is what we have for this. I think that the best will be a stop around here, or allow you to play a little bit. And this afternoon, we will be showing a little bit of this with Keras. Keras is remove all this complexity of linking this, and you just, with one line, you create the layer. It will produce a much higher level representation of this problem. So it simplifies how you create this kind of neural networks. One, Keras. And by the end, I will present a little bit of PyTorch. I will show you how with PyTorch you can basically do the same linear algebra that you used to have with NumPy, but this time happening in a GPU. That's one thing. And I will show you how you use PyTorch to compute neural networks. There are several neural networks packages around, so I am just having a small selection of just the most frequently used when you see on internet. TensorFlow, PyTorch. TensorFlow was from Google, I think. It's from Google, right? PyTorch is from the people in Facebook who create that. They allow you to do things that you cannot do in TensorFlow. So you see, and you can see why the design is so different. And in this TensorFlow, you declare those, at least as far as I know, the new TensorFlow, they have these capabilities added to. But you prepare the model, and you declare how many neurons you have. And PyTorch allow you to prune networks and remove networks on the fly. So when you are in the middle of the operation, you can take networks out, put them back, and do that kind of stuff. It's I think that they implement that in the next version of TensorFlow. I couldn't find the way easily to install the package for TensorFlow 2.0 beta, the version. So I was restricted to use the 1.14. That is the latest stable version. I don't know why this virtual machine is offering.
It's just you have your channel order. We need the wonderful version.
Ah, is that? Or in the Intel one? Or
yeah,
the
just
Intel.
change
The channel, and I will get it. Okay, is that? Okay, yeah.
You can do that now. You can do that.
Yeah, we can do that during the lunch to see if I can get something. So yeah, take your time, and we will come back for those topics, for Keras and PyTorch. Yeah, we are fine. We're fine.
Back at 12:30 or?
At 1, so I have time to play to see if I can get this with new version. Or eventually, something that I can try is to demo in you. When you have your accounts on Thornyflat, you can have access to those GPUs there. They are really good. As far as I know, they perform really well. Yeah. Our new GPUs on
Spruce?
no, on Spruce we have those, but they are kind of old. They are Kepler generation. On Thornyflat we have Pascal generation, so they are much better. Peak 6,000, right?
So I don't know. I know that I run the same thing both ways. In one of them I get 40 milliseconds a day, and the other one I get 120 milliseconds a day. Spruce is
So
20
moving
milliseconds
atoms,
a day,
you know.
because I run simulations of like 50,000 atoms. Yeah, and so I have the same engine and everything. In one of them I do 40 milliseconds a day. In the other one, in Thornyflat, I do 120 milliseconds a day.
So it's almost what, 20 times, 30 times faster. It's like a factor of 30.
5 times faster.
5 times. Yeah.
The only thing that you have to be careful with is, like if someone has so many community queue, you can only run so many Thornyflat. You can only run so many in the. And so, like, if you have a group, for example, our group, we run like weaponized simulations. There is 4 grad students, and each of us runs easy 50 to 60 simulations at a time. So then we have to figure out which queue we use so that we are not overloading both queues at the same time, or like we are not waiting for forever for our colleagues to finish the simulations, because we run them for a week, most of us. So, but no, they're fast.
Using just one GPU or using the?
Amber, you can only use one GPU.
You can only use.
I use Amber. You can only select one GPU. You cannot do one.
So it's a third.
For NAMD, you can actually run on several cores.
So that's what I will try to do here.
That's the normal need. The thing is that the NAMD that we use, the version that we use, kind of like CPU, but like parallel CPU processing. So you can run. I think it's my sweet spot so far has been running on 32.
Okay. So yeah, what I will try to do is on showing you without the graphic interface. I don't need actually that for this kind of problem. How you connect to Thornyflat and running that. I will be preparing that during lunchtime to show you either PyTorch or TensorFlow on our GPUs. This is really good. And most of the people who uses the GPUs are basically you, Blake's people, and just a few people in playing with neural networks in engineering.
Well, and Aldo. Well, he doesn't run the GPUs.
No, Aldo is allergic to GPUs. No.
Yeah. He will run everything on parallel CPU. Yeah, we run everything because, like, with Amber, for example, for me, or Bromax for Eric.
No, it's because for DFT, there are some advances on that, but it's for my area GPUs. It's not that fancy.
Yeah, see, I use Amber precisely because of, apart from the force fields, is because with the PNE-ND.CUDA, I can run microseconds within a few weeks.
You are not using the GPUs at all, right? No.
I back myself into a corner on that.
You don't want to use them because it's another problem that you don't have time for changing
the problem with the way I wrote it is like on the LJ coefficients, and LAMPS has a special code that does long range calculations.
Only for CPU you can do that.
Yeah, they don't have it for the GPU, and then to rewrite it in GPU, LAMPS isn't friendly. You code the whole thing. And
Okay.
it took like a long time to figure out if that was equal to the other ways that we're doing it, and like, you know what I mean, like make sure it was right. And
yeah, you are in that side of the sigmoid when all that you want is to graduate. So yeah,
I think
We are
in
there.
the future with certain things, I might just run Romax because it's a lot better with GPUs.
It's a lot faster. The only thing is that obviously because you're basically getting
Nate,
every
should I stop share for a while?
Stop sharing it. Stop.
atoms at a time. You're
Stop sharing on.
So for example, like we try, you know, we try to calculate technical angles and stuff like that. Or like physical component analysis. It's kind of difficult to do.
Romax doesn't do
Oh. Okay, so let's go back. So we will be talking about PyTorch. So PyTorch is another library aside from TensorFlow created by people on Facebook. It works very, very close to NumPy arrays for most part. So you can use it as a replacement of NumPy for big arrays or for deep learning for training neural networks. So, and then this is the traditional block, executable block that you use. Now this time, I mean, this is how you import Torch. I hope I have it. It's still installed. Oh, wait. Uh-oh. Well, anyway, I will explain what I'm doing. I installed PyTorch, but the version that I installed by default was the version with CUDA, and this virtual machine doesn't have GPUs on it, so it crashes from the very beginning. So I was now installing with CUDA specifically, not this one, those one, the CPU-only versions, forcing exactly the version and the build tag for it. So that should allow me to do this. Yeah, now it's working. Okay, that means that probably I will have to reload this. Okay. Well, I am using a lot of memory. I will have to kill something around. Okay. So now I import Torch. I have to remove and change the version that I have that is working. So notice that it's very, very similar to NumPy. I'm creating a bunch of zeros in an array 4x4. It looks like this, very similar to the new NP zeros in NumPy. This one is new. NumPy doesn't have this functionality, but you can create arrays without zeroing the array from the very beginning. So it's basically capturing the garbage, whatever it was left in that position of memory. At that moment. So you see that the values are not actually zero, it's whatever the garbage was in the memory at that moment. Random numbers, very similar again to NumPy. Integers, same thing. And now arrays. So in this case, arrays in PyTorch are called tensors. So even if it's just a vector, so we can create explicitly a tensor. All those are tensors. They are called tensors. But you can create them explicitly from a list. So that's exactly what I'm doing here. And you can also change the type. Remember that we change types in NumPy arrays, and we indicate that we want something to be an integer or floating point number. So now these times you have to specify a torch data type. But other than that, it resembles a lot of working with NumPy arrays. Zeros. So a new array with the garbage. So you see at this point it's very, very similar to NumPy. And you do all the operations as usual. I never show that, but addition, multiplication, element-wise operations were exactly the same. Yeah. So here I am. So here is an array, another array.
The only advantage is that it gives good.
Yes. The big advantage is that even from the same perspective, from the same natural way of working, NumPy is only for CPUs. Only work. Here you can say, I want this operation to happen on a GPU. And I have this memory to be on the GPU.
You don't need to say space.
You can say that split. So right now it will not happen because I'm using a CPU only. That's the whole reason why I have to go back, install, deinstall, and install again, forcing the specific version because this machine doesn't have a GPU. And that was exactly what I was doing before on Thornyflat, because I would like to show you how efficient it is with the GPU. The GPUs doesn't work very well. Okay, NVIDIA doesn't work very well with Apple. They don't get along. They are so it's a nightmare to get CUDA working on a Mac. But on Linux it's okay. And on my computer it makes quite a difference. So that's why I would like to show you that. But let's see what I can do. But right now I can play with this just from the CPU, and it will be fine. So addition, same thing, nothing outstanding. There is something here. You can do those operations by overloading the operators. Something that you can do in Python. So decide that you want this to be an operator, and it looks naturally like that. Or execute additions or multiplications in a more functional way, like a function with two arguments that they compute this. It's the same. So again here, this is an operation again in this some way where I would like to have the output written in a different object. So I created the object. This object contains garbage, and when I add in executing the operation, I want the sum of this plus the sum of this stored into this one. The reason why people decide these kind of things is because we are planning to use this on GPUs. So it's okay doing like this here, but on a GPU, you don't want to bring the data from the GPU back to you. So you want to execute this plus this, but put it there. I don't want to see it. So that's why this kind of operations exist like that. You don't want to see the solution. You just want the solution to be stored in something that is quite hard to access in terms of efficiency. So same thing, this operator, this is exactly the same as this one. Adding, and this one, those operations with this underscore are added in place. So you have Y, this array, and you add X, and the answer will be again on Y. So what else? Oh, remember last week when we were playing with NumPy arrays that we can move and jump to two columns and or reverse the order of the whole array. These kind of things we can do here, exactly the same as NumPy. So just to make this visible, I'm making an array of 64 entries, and I put them in a 8x8 array. So I can see that all those operations that I showed last week, like jumping by two, work equal. So here I'm selecting this one from 2 to 5. So this one and this one. So that kind of things work. And changing in place. When we do this kind of things, you are changing in place. So I'm deciding here X to be like this. This is not in a different location of memory. It's the same array. So X and Y are the same array. Y is just a view of X, where you are just selecting 3 columns. But all the memory is the same. What I did here was changing one element in Y using the indexing that is correct for Y. So this value here, Y00 is this one. I change it into 100. And here I am looking at X again. And you notice that the value changed. So those operations, this operation is not creating a different array. It's just a different view of the same array. So exactly the same as in NumPy. So here, I'm looking at the object, what are the sizes of that. So they return the size of all those arrays. So the original shape they call size, but it's the equivalent in shape on NumPy. They will say 8 times 8. This is a view of the array, flatten it. It's a single array of 64 elements. So the size, the shape is 64. And here is a view of a few elements, the last elements. So it will be 4 times 16. So at this point, most of the operations in NumPy have an equivalent on the other side in Torch. So the idea is to have something that is very, very compatible in the functionality. I already did something around this, so you can extract elements explicitly. They return as a tensor, even if it's just to return a number. When execute this way, Y is also a tensor. So it's like a tensor of rank 0 tensor, which is a scalar. In order to get the actual number, you have to execute this operator on top. So this one becomes the integer of the value that you use. Tensors are also able to be converted in the natural data types for Python, the low-level data types, in this case a list. So you can convert a tensor back to a list, in this case a list of lists. So that's okay too. Something quick, we can go back from tensors to NumPy arrays and the other way around, so both ways. So here I have a tensor, I create a tensor again. I'm basically recreating my in a smaller version, 36, 6 times 6. And I have this tensor. And I have this operator here to convert it into a NumPy array. So, okay. I will not have opportunity to show exactly this. Again, I already showed this, that you change one element is changing the other, so this is nothing new. But on a GPU, it's interesting, let's say. They are preserving memory location, so you change something inside, it will change outside. There is some consistency there. NumPy arrays, random numbers. and you can convert from a NumPy array back into a torch tensor here, and you can change the values of that, and that is equivalent. But so a very quick introduction just to show how both NumPy and PyTorch share a lot of functionality up to this point. So now we will use this. This is something that I will mention it quickly, because we need this in order to make the neural networks to work. So let's start with this. The idea here is that Torch is able, for a tensor, you can indicate Torch that trace back the operation that you are doing in such a way that they can compute the gradients when they backpropagate the operations. So there is a difference between creating a Torch tensor with or without this flag here. So this flag will indicate, keep track of any operation that I do from now on this object. So I'm creating here a set of ones when I will be tracking the gradient. So here I am adding a number element-wise. So you will see that I have the gradient function. This is computing what is happening on every single step. And I have here a function that is collecting all that information here. So the backward gradient of that. And let's do more operations here. So here I am taking the array, this array, that was this one plus 3.14.
You have,
yes.
you have the value of the gradient?
They collect that into an object. I never actually saw that. Let me see.
Oh, I can use it, of course.
Yeah, you can use it, but what exactly they have?
That's fine.
Yeah. So I'm taking the square plus this function. So I create. This was not what I meant actually. Like this. So a quadratic function. And again, I'm getting the tensor here. I am doing this with a matrix starting from ones for a purpose. But so we will see exactly what we're doing. So I have here the subject here and the tensor and the grade. And after all those operations, the square, the polynomial operation plus the translation that we did, we can backpropagate this, the gradient. So this is what we are doing. By the way, here, what I'm doing here is activating on the fly after the object was created, activating the tracking of the gradient, even if the object is already there. So this is what I'm doing, enabling here. So at this point, the request gradient returns false. When I activate that, it will start tracking the changes. So here, I have this object here out that is computing the average of this object, Z. And I can backpropagate that. It changes because I made the difference here. I was making a plus. So basically what it's doing is, if you do this and you follow what all those operations are happening here. So this, and you replace y by this, and after you start by hand, you can do it by hand, taking the gradient. So in this case, it's just, we have just like one single variable here, so it will be the derivative of that. You can trace back and you will get this. So the difference here is that this autograd is doing the hard part numerically of tracking the changes. Every single operation that you are doing, it keeps track how they will revert that to compute the gradients. So this is a very, very small example of how this works on a CPU. So here I am adding, for this case, what is this case? I'm preparing the network like this. One layer here on a convolutional network, another layer convolutional, a few layers normal. So it has 5 layers here. So this is how you build the neural network. Very, very clean, let's say. So here is how you propagate, how you declare the activation functions on each layer. All of them will be the linear activation. So this one is the entire set of operations that you have to do when you are forward propagating. Let's say when you are moving from the inputs, as we did for the example that we did by hand, moving from the inputs into the first layer. The input will be this, the input will be X. So this will enter here in the first layer, second layer, next layer, and they return X. So they move forward the network. Here, what I'm doing here. Okay, this one probably, yeah, this one is because what I'm getting is an array, and I'm basically flattening that array. That's what is happening. So, okay, so you declare this. Nothing is computed at this point. You have the machine on top. So the neural network, they will tell you the layers that are involved here. And now we can start using this, the parameters.
It's a little bit more complicated than Keras, right? Keras is smaller code.
It's simpler when the first example that I show you. But remember that then after that I show you an example with convolutions. That there was, this one is using convolution. So you have to compare this with the second example, not the first example for them. The first example was where I made the mistake and I create the layers, but I linked the layer wrong and I was keeping one, doing nothing, losing one layer. So yeah, I'm trying to get where I am start getting this. For the day. I am missing something. Something is not complete here. The training is not here. Okay. Yeah, there is something that's missing. Okay, so this is PyTorch. It's relatively simple, but yeah, it works different from TensorFlow. The other alternative is this one, is Keras. Keras sits on top of TensorFlow or some other neural networks. They support like 3 different machineries on top. They basically simplify the creation of the networks for you. So let's see how that looks like here. And there are 2 versions. There are the Keras that is an independent code and work with different neural network engines. And there is the implementation from the people of TensorFlow of Keras. So they have their own Keras implementation. So that's what I will be using here inside the TensorFlow. So here, this will be a simple perceptron. This is a very minimal example. So again, loading the iris test. So we have, I will be keeping just 2 features here, all related to the pedal. So my entry will be just 2 numbers. And the target will be just if it's one of them. So here I'm creating this, 1000 iterations. This is my tolerance random set here. And this is, again, very similar to how scikit-learn works. So you prepare the machine is this one, the perceptron. It's on scikit-learn. And here is what I fit, and this is the prediction. So this is what is implemented in scikit-learn for doing perceptron. And remember that perceptron is one of the 2 things that where neural networks evolve. So it's just basically a linear classifier. This is a linear classifier, actually. And not only linear, it's binary. So they have just iris or not iris, and it's doing the prediction for that element right here. The same thing here. So it's this. A linear classifier between being setosa or non-setosa. So a binary classifier with a perceptron, and a perceptron is like a neural network with no hidden layers. So all that it can do is to have the number with a weight, sum, and eventually an activation function, but the activation function is relevant. It will just produce an output, and you change those 2 weights, and you get the output. So a linear classifier. Activation functions here. So this is how you can define with NumPy the 3 activation functions that typically you use, or well, at least the sigmoid and ReLU here. And this one is how they look like, the activation functions and the derivatives. So now we will use this machinery with Keras in order to predict the iris database. I create this for 1.14. I hope this works with this version. I never change it. I never have time to change it. Okay. But this example will be will be slightly different. Will be for the fashion emis. Let me see if I can get it. So this is a different database. It's 60,000 elements of grayscale images, 28 times 28. But the problem is harder. It's, let me see if I can show it here. But there you are. They are trying to classify figures like this. And they have a bunch of them. Let's see if I can get all of those. are right here instead. Okay. So this database contains 60,000 elements, images 28 times 28, but they have far more different entities or different classes to play with. So you are trying basically to identify those different elements, right? So they have these classes, and they look like this. So here we have this model. This is how you program this in Keras. You will see that it's very, very, very easy, let's say. So first, this is the input layer. We are taking the image and we are flattening the array. So this is what we want to do with an image. Here I entered a dense array with 300 elements. I enter a new layer here with 100 elements, densely connected to the previous one. This is the activation. So in one line, I create the whole thing. And it will be, Keras knows how to connect those things. In TensorFlow, you have to do it explicitly. Remember that I create the network, and I put the activation function was in another line, and after I have to link, and after this is happening just in the way I create the stacking of layers, sort of. And here are my 10 solutions, and I changing it to a different activation function. So this is how you define the model. Let's see. Oh. I would like to share this with you. Okay. What I did here, the problem here is that this function have changed between the TensorFlow 114 and TensorFlow 110. I wrote those things and I test them here with 114, and the function have changed. So it was before tf.random set seeds this, so I have to go back here and see what has been the alias before in the old versions of TensorFlow. And otherwise it was not a big deal. It's just that I will get different numbers because I will not initializing forcing the initialization of the random seed. It's not a big deal. So here is my model. And here is the description of the model. So a flattened layer. So an image converted into a flattened set of points. One dense, one dense, one dense. And I get out after that. So here is the summary. Okay. The summary is okay. So I enter with the image. The images are again 28 times 28. So this number of elements in the array. I am connecting this densely. How you pronounce that? Dense with this. And from here to here, another dense connection. And they are counting the number of parameters that we have here. So we have 748, but 4 times this one, so you get this number of elements here. Plus probably, I'm not using biases, I think. No. So this one and this one. So the total number of parameters is this that I'm feeding. And this is exactly the total number of train them more parameters in this, which is at the small number actually. So some big neural networks use billions of trainable elements. So this one is not that bad. I'm not super sure if I can plot this if I execute it. This needs GraphBees and other packages. So I will not execute this box. But if you have the package, if you have GraphBees installed, Keras is able to plot this in an image that you can export, like a figure, just in case that you want to show this, the structure of your network in a figure for publication or whatever. So I will execute this. We can see each layer what it is. Yeah, I don't think that I have bias here. Yeah, I don't have bias. I never declared that. So those are the matrix of weights for the first matrix here. So remember that here we have this times this. So it will be a matrix when we move this. When I did this, some linear algebra operation, it's a matrix of this times this. So those are the weights. So this is actually what the asset that it costs, that is very valuable for those companies who mine this set of numbers. This is what they kept and cost millions to get those weights. When they put this into the right network, so you get the solution. By the way, those are the random numbers, so this is not the actual solution. This is just the first numbers that we create. We have not yet put the model into training. So here is where we are starting adding the known data into the process. I will change this a little bit. Let's see how that goes. So I will be processing this with the whole data. What I would like to track is my accuracy here. That should be improving. By the way, do not compare those values with the digits. This is much harder. The classification of this is tricky. The grays matter most. So here at this point, we are around 80 something, 88, 87, 88%. Not that bad. I think I can search here in OpenML. No, I don't think so. Okay, so here the good thing is here in OpenML you can select, for example, one data set, and you can see what people have done and what they have achieved with those data sets with training neural network, for example. So I was looking at this, what people have achieved in terms of accuracy on this. So you see that around 80% here are most of them, between 80 to 90, and there are a few here when they achieve what this one here achieves. Show me that. 99%. Using how many layers is this? They did quite a number of things here in this complex network to achieve 99% of accuracy. I don't think that I will get something that good with this single thing.
Mine is giving an error.
Maybe memory?
No, saying that the dimension of the input is wrong.
Let me see.
3-dimensional is 11,000. That is if you change something that I did.
What I changed was I put actually more people.
I put my model.
This is very happy. That's so let's do this. Or go back and visit the phone. And okay, they stop here. What you can do is move this line into a markdown line, or yeah, put something in your comments. Just to avoid it. And maybe 5. So it's not that you're doing this in Colab.
No, I didn't.
In Colab,
No.
or in the other. But if you are doing that, why your notebook is different?
Huh?
Your notebook is exactly the same. You have those nice. You are in training. Yeah. Yeah, I'm doing. Yeah, I'm saying. I don't know what this looks like. Or maybe because I scale it, I enlarge the screen, and maybe that's slots. So what I'm getting here, 50 or 50. What I achieve, almost 90%. It's not bad, but it's not outstanding when you compare with these others. So it should be something like this. This is a different classifier. So, okay, so with this, you see that using Keras is really, really easy for entering this. So all the machinery, forget about this. This is just to show things. It was basically this. The definition of the neural network was this, just that. Much better than the other, the TensorFlow description. The training was here, the fit. Okay. And you can get this history. There is something nice that you can do here. So with this, I can collect how my accuracy have improved over the epochs. What is that? So here, you see how I am moving this over time. So yes, with more cycles of this, with more epochs, we'll probably get a little bit better, but it's asymptotically very slow. So it's not improving on that. So the next thing that I could try to do is to add more, either a fatter neural network or adding more layers. So the idea is always trying to do that. Let's say we're talking about that. It's not trying to use the most complex neural network to achieve the problem. It's just the other way around. What is the simplest solution that gives you something that is reasonable? So,
is it possible to save the?
You can say both. Yeah. Actually, I will do that. You can say the model, or you can say just the parameters, because just the parameters is not enough, because you don't know how do you connect those things. So just the weights you will not have the picture. With the weights, you know that this layer has this many entries, this layer has this many entries, but it will not tell you which activation function you did. And probably if it's not fully densely connected, if you have pruned the network, you don't know what was connected to what. So there are ways to save the model or save just the parameters and load it again. I think that I will be doing that in a moment. So I am showing you just the figure. Okay, this figure is there. Originally, the execution was meant to be for a long time. So I will skip that. And here is how a prediction for a particular object looks like. This is how this classifier works. So I have this object, 3. Let me see. How I can see this. Yeah. This one, right? I'm taking one of the elements and I'm plotting the figure, how it looks like. Is this one? And I ask him, okay, what is the prediction for that? And I will get something that is either very small or very small. And I got here 0.99, let's say, probability of being this, or this, or this. So this one is pretty confident about this element. Here they have 2 options, but they are remarkably different in value. So, and here is basically this one. So the classifier basically puts real numbers for every single instance, and it just takes the higher value. So there is something here that will show you about that. Yeah. So I was plotting this one. Those are the 3 elements that you see here. So this one, it got it with practically on 100% accuracy, confidence on that, 100% confidence on that. And this is 99 for this one. Okay. So this is another example out of images.
Just a second.
Yes.
So it's saying that the boat could be one of these 2.
No. It's this. This is what I did. Here I am taking the first 3 elements on my set, and I'm asking here, okay, give me the prediction for those 3, and I will get these 3 rows of numbers.
No, I understand.
Okay, so, and I just plotting. I was plotting just one of them. So if I change this one should be this one. The colors are, or this one. Just for you to see what they are. So it got slightly value for this one. I don't know exactly what it is. I need to check the names.
Oh, that's fine. That's fine.
But yeah, you got the idea. So are those. So this one is a slightly different example. Without those convolutional things. And are the housing pricing from California. Also, again, easy numbers. It's working. Yeah, it's request. Okay, this one will again fail for this. So now it's okay. So remember that I removed this element random here. due to the version of TensorFlow that I'm using. So here, this is a simple example. One layer here, one single output here, densely connected to the previous one. So what I want is, I think, is just trying to figure out the price of the house from the entries, the different parameters for that house. How many? 20. It's not that bad. This is super cool. Okay. And now I am plotting the history of that. And what I'm plotting here is what's the loss? The error. The mean square of the error. That's what I'm tracking here. So this is how that goes down. And the values are just real numbers. I don't know exactly what they mean. Here they are doing something slightly more elaborated. Same thing. The input here, first layer hidden, 30, 30. Here, they are linking the input directly to the second layer. So this is slightly different. So instead of going in sequence, there is a link that it goes back to this one. Yes, and here goes the output. And here they're creating the model. So let's see how that looks. Just summary. Let's see if I can. If I see this. Like this. So here is the input, first layer, second layer, jumping from the first layer into this one, producing the dense layer. I will not try to plot this with a figure. Let me see how that goes. And I am tracking the error. So it's a curve that should go down. So I can actually borrow this one here. This is the behavior of this one. New one. this one has a feedback rating. Input layer here. Another input here. One layer connected to the second input. This layer connected to hidden. This layer connecting the first input here into the second and the output. So it's harder to figure it out how we are connecting this. What I'm doing here. Oh. I don't know what it comes from. Looks like a bug in that. Okay. Yeah, I'm hitting the same problem. Okay, I will skip that. Your question. Saving and restoring models. Let's go back to something simple. I'm using the 1.10, and there is something here that doesn't make sense, and it's not in my code. It's in the inside the currents.
I need the save.
The save is not working. Let me see. Okay. Oh, yeah. This is my fault. This is something that I will fix. Is this package that is missing there? Hmm? Okay. Yes. So I will have to record here this one. Was this one? Ah, no, was this one? Actually. Yes, yes. Okay. So this is how you save it. I just need to install a package and it was not reloading the package. So, so if you want to get this, you have to restart the kernel and basically but for some reason I was trying to load the HDF5 library and was not loading. So I have to kill the kernel and force it. So you execute this one, this block, this first block here. After you execute what is about the California pricing, whatever. That is around here on top of this. Yeah, here when it says regression, you execute this block, so you will get the training set, the validation sets from the housing. And here you go back here and you can create this very small neural network, 3030, and you save it here. So you are saving all the numbers here, all the models, all the metadata in HDF5. So it's a file format for storing binary, large amount of numbers. And in this case, those could have a lot of numbers. So this is a very effective way of storing that data. There is nothing proprietary on this format. So this is an open format. Any Python with this library can open that format. It's efficient and it's open. There is nothing that constrains you on that. And I can imagine that I have this file, but I never create a model. So I can recreate the model from the file here. And I can continue predicting values. So this is what I said. It should be around here, I think. Here.
I think
it's not that.
Keras is it's multi-platform, right? You can have on C++ as well, multi-language.
I think so.
So
Yeah.
you can get
But I'm not using the Keras, the original Keras implementation. So there is a difference. That's slightly different. So there is one that is Keras here. You see, let me see, this one. This one is the whole package that supports TensorFlow, CNTK, and TN. So different engines for neural networks. This is different from TensorFlow having, what is this? The API here. The Keras model. This is an implementation inside TensorFlow to work like Keras, but specialized only for TensorFlow. So, okay. So we say the model, we load the model, we predict, and a different business here, but you can say also just the weights. So just the matrix of weight. And this one is. Another missing package. This one is tricky. This one I cannot figure out, so it's something is not right, saving the weight. Let's see. Another simple model, same thing.
I fixed them. Just put dot slash. There.
Where? With that.
Saying there is no parent.
Oh. Okay. Okay. On the new version, they don't have to do that. They put the dot slash. Yeah. Okay. So here again, I created a very small sequential neural network. I'm training here. What is this? not able to capture this. It's not working as I was expecting. So the idea here is that you can decide that you want to train for a certain number of steps, and you can to stop at certain point, check the values, and continue. So doing like a debugging of those neural networks. But for some reason, I had to remove the argument that actually was doing the stopping. Yeah. Okay. Okay. The last thing I was trying here. Let's see. Okay. I will probably not be able to actually train a network, but just for you to show you that this is Thorny Flat. This is one of the compute nodes on Thorny Flat who has CUDA on it. So here, Torch, you import Torch, you are able to see that CUDA is available. You are able to see how many which of the several CUDA cards is working for you, how many you have activated for you. And something that I can do, let's show this by Torch. Is this. Huh? What?
What box are you?
This one. Can you see something in the NVIDIA SMI?
Try to.
They are in usage?
Yeah.
Okay. When I enter, I check
Go
it.
double check.
Yes, someone is using that. I cannot show that. Okay.
Try one. One's not me.
Okay. And the one I got.
Just keep you. Did it work?
Yeah, it should be, I think.
Looks like it's working last time.
Yeah, it should be. It detects the tree, but it only allows me to put this array here. So yeah, here is. Notice that when you execute this kind of operations on machines with CUDA, you get the array and they mention where in memory, with which machine is holding that array. So all this operation was happening on the GPU. Actually, not the most efficient thing to do, but another thing that I could try eventually is this. Let's see. Let me see if I can do this experiment. Remember that we
create
what?
environment.
Yes, that's what I was doing. Let's say I create a conda environment here quickly during lunchtime. And I call it that way. I'm not really sure if I create it for me or centrally installed. I can always create a new one if I need it. And I installed PyTorch, Keras, and TensorFlow. So I installed the trinity of this for GPUs. And I have another one where I disable the GPUs. It's a pure CPU. You have to switch back and forth.
Every machine on this cluster has GPU.
No, just 6 or 7 machines have GPUs.
I know a machine that has GPU.
How you what?
Oh, I know. I'm on a machine that has GPU.
Well. Typically, you're not supposed to worry about exactly which is it.
So if I run something,
PVS.
you go to the GPU.
You request the GPU. The GPU, and it will only go to the GPU node, right? I have to. What?
You're on the. You have to exit out of it.
For doing what?
Get you back there.
Oh yeah, but for example, if do you know the command for
qsol?
Do you know exactly the name? Imagine there's this one, right? And after that,
everything was one, PPA one.
with like this or like this?
No, column.
Column.
Just like you did PPA.
I can ask for 3.
That equals 1. No, you can't use it on
Okay. Yeah, I got that, and I check with this and the.
Okay, so you need.
Oh, it's not nice. It's not looking nice. But
That's right.
That's correct. Quadro is a card, right?
Yes. Yes, it's one card.
It's not human friendly.
A what?
It's not human friendly. How to log in this?
To get access to that?
Yeah.
Well, it's not that bad. It's,
What's that to me?
yeah, it's not as user friendly. That's why we like to have this Jupyter Hub, this open on demand. It will be really, really good if we can offer this nice environment where people just sit in a browser and start executing those things and training. This is kind of low level. So yeah, I agree with you. Yeah.
If I need help on this,
But then again, if you are training a big neural network, you will not sit down in front of that and keeping your laptop open just to run that. You program something that you submit in the old way. Because that will run for days until you get something. So at some point, you cannot rely on the nice graphic interface. For this exercise, academic exercise, 30, 300 nodes, yeah, it's okay. But for real research, yes. So let me see. I was trying to open this. Okay, this one at least I don't need data for this example. So this one is like this. Let me see. This is out of the Jupyter environment. I can probably secure it similarly, copying and pasting these lines on Jupyter. So this is what they are doing. They have a polynomial here with some random numbers. Where did I do so? Here. Where is the model? It should be right here. This is extremely simple because this is just a linear classifier, or linear regression actually. So they have the values here, the answer, they execute this. There is no data that needs to be downloaded. Unfortunately, I cannot download data because I'm not a compute node. and it's basically trying to predict the weights, so the parameters of a polynomial in this example. This is part of actually of the examples. This repository here is the official set of examples for PyTorch. So git remove show. So if you have PyTorch on your computer or something,
That's not gonna work.
it's not. You need to connect to execute this command. I was not expecting.
You can get the storage. Git remove get web URL.
I'm trying to get what is exactly the repository for it for that. So anyway, so it's this one. It's this repository, and they have examples in several languages, and they have this example that I was trying to do, but it's downloading the data, so something that I cannot do there. And what I execute was this regression example. That is to say.
Let me ask you something. I didn't understand. So you have Torch, you can run the same code both GPU or
Yes.
CPU, the
Yes.
same code.
The same code, but not using the same PyTorch.
Okay, understand.
So what I did was I have two different conda environments. One with the package, all the packages GPU enabled, CUDA enabled, and all the packages without CUDA. We just have 7 machines with GPUs. So with the CUDA toolkit installed. So when we try to run, for example, in the head node, they don't have CUDA, they don't have the CUDA toolkit, everything fails. So that's why I have to play tricks with that.
Like something now is GPU.
Now is GPU. With the conda, I am managing that. But
Code.
the code, no. You can. There is something here in
I'm assuming
Python.
you will be calling just the version that you're running it with, similar to what we do, is whether it is PNEMD or PNEMD.CUDA. It will be the same thing for this, right? Whether you
Yes, but this
selected
time
CUDA at the end
changing
or not.
the code, the conda environment. So it will.
Yeah, so
Because
it will be
I'm not
conda
using with
.CUDA or
modules.
something like that?
Huh?
It will be conda.CUDA or something similar where you select the CUDA environment in conda rather
No, so let me show you what I have. So
this is
conda,
what we do. We have the same code, but it's just depending on which version you're running, whether you're running in this version, where you put
yeah. So but it's similar to this. So, but you are talking about the environment modules, like we have for LAMS, for NAMD, for Amber, but here those are conda environments. So I activate conda on my terminal first, and I have this set of conda environments. Some of them belongs to me. Those that are which one? No, actually the other way around. I create this centrally. I install them with build, so everyone can see this. If you have accounts, you can see this and trying to execute this with your accounts. Those here is something that I create, so they are located on my home folder. So only me can act. But anyone can create its own environment and can use it. What I should be doing is put this neural, the same state as the neural dash GPU, to have exactly the same packages with GPU, without GPU, for Keras, TensorFlow, and PyTorch. Yeah. And the thing that I would like to show is that using the GPUs changed a lot how they move super fast in those epochs. They move extremely fast, but unfortunately I cannot show you that. Okay, I think that closes the session. I show you a little bit of everything around. So it was not super deep on anything, but we travel up 3 packages for machine learning and neural networks, all this stuff. The only thing that probably is trickier here is when you move into the real research and things are not so plain as prices or things like that. So you have to think about your cases and how you manage, how you design features for chemistry, for physics, for engineering, for that is where the value of the research actually is from. Running those things is just like a black box, and you run it and you get the numbers out of that. It's how you tell the machine where to put the atoms on that system, or where to put your particles, or how to capture the movements on robots in your case. Yeah.
Can you not connect to talking flat? I cannot connect. I connect once, but I cannot connect.
Let me see.
Are you using the?
So I can do it here. I can do it here. So let's actually do quickly that. SSH, Franco. So you use your own username if you have it, and you can ask for counts. So at some point, and when you ask for which cluster, click both. It's free. So asking for both. Don't worry about that. Actually, you make a favor, because if you again have to request another ticket when you want the turning flat, we have to execute again. So ask for both clusters, and it will be fine. So SSH, right? WVU.edu. So the password.
It's asking for.
Huh?
Yeah, it will ask you for the.
But this is not.
That's not Thorny, then you have to log in.
Yeah, this is not Thorny. This is the first part, the first step. Do you recognize why this thing is doing this? Asking for the password again.
Let's do factor log.
I think that one happened.
What is that? What actually should be entering? The my password or the code?
I don't use no external. Cancel that.
Cancel. Yeah, this is weird. Not. Now it kicked me out.
Yeah, that happened.
It does that to me a lot, actually.
Yes.
Like every time I try to log in, it kicks me out and it tries to do it again.
But you are using Windows?
Using Mac or Linux or Red Hat.
No.
Why does it happen to you? It has never happened to me.
Like almost every time I log in for the first time I open that terminal window, almost every time it'll like let me put in my password and hit Duo, and then it'll say rejected or rejected my remote host, and then I hit do it again, and then it accepts it the second time.
Actually, that happened to me once.
Yeah, it happened to me 8
That
times.
kind of thing is in our control? No.
I have 8 fatal logins here.
I can't remember if it was like an update that you guys did or something like that.
We don't control this.
There was something, because we got an email saying that it was going to change slightly how you connect to this, and it happened right after that. And then I think I can't remember what I had to do, but it was something I had to do once, and then it automatically does it everything.
Okay, so
But
now,
it was because it
So now we're in this getaway machine. So
this cannot do anything.
this machine has not do anything. This machine is worthless except for putting them in the middle of you and the actual class, because the cluster is in Pittsburgh, so we have to use this kind of. So now I execute this. Let me see.
Get with -X to get.
Yes, but I will not be. Yeah, if you want to, but I will not be using that for. I will not be using the X. If you want to use this, let me see. Do I have the X? The X here?
I put the X.
Let me see. Maybe they are here, but they're here. Okay. So yeah, so I have this, and if you want this, okay, yes.
Yeah, I did that. Yeah, the problem I had is that I was the first time I did that, but then it started kicking me out 8 times.
Okay.
On SSH, not on one.
Yeah, but anyway, I will not be using the X11. So now I am on Torney, right? On the head node. If I want to execute, for example, Conda, and I can get the trick just with this. This is actually not doing anything. It just gives me the line that I need to execute. Is this one? This line. This line, you copy and paste this line. Is all that you need to get Conda activated on your terminal for this session. Right? It's working. You have this thing.
I have everything working.
Base here on your front.
Why does it say bioconda?
Huh?
Why does it say bioconda?
Yes, because probably copy and paste the module from Spruce, but we should remove that. It's just
something special.
No. Conda is just bioconda is just channel. So yeah, you should not call in this bioconda. It's just we created thanks to that people from people in biology. So we should use this, but no, there is nothing special. So here. So next thing is I would like to see which Conda environments I have available. Conda and list. And I have those, right? And now imagine that I'm not happy with what the administrator did with those packages. So I'm not happy with myself. So I would like to create my own environment. So
your GPU, it's good for doing everything you need today?
Yes. So if you are sitting on the GPU machine, use this one, but you can create this one here. So I will create a new one that we'll call NN. Or do something, do yourself a favor. If you plan to use this for serious things, you will have to move your Conda folder. This folder grows pretty quickly because it contains all the packages that you install. You only have 10 gigabytes. You install packages and you grow these things out of control. So what I did, probably you are fine if you are doing the first time this. What I do is move this .conda folder to a scratch, and I create a symbolic link here. So I move that. For me, how big is that?
They have a ton of small files, so it's
Is what?
Conda has a ton of small files.
Yeah, probably will sit. Yeah, 10 gigabytes. So I cannot keep my Conda environment on my home folder because I have some other stuff. So I don't have 10 gigabytes free for hosting that thing. So now, Conda create -n, and I will call it what? No, NN. I will create my own environment. It will be empty at the very beginning. And it's asking me, okay, do you want to install this here? And I say, yes, it's a symbolic link. So .conda is a symbolic link that's somewhere else. I don't care about the space there. So I have now conda, if I execute conda and list, I will have this NN right here. Nothing in there. Conda activate NN. And now I have this new environment. Conda list, no packages here. New environment, clean, nothing. And now I would like to install PyTorch, just PyTorch. Conda search. And I got this. Let me see if I can do for. Probably cannot do much to make it smaller. But you see, there are a lot of versions here of packages. This is a tricky thing. For this one, either you know exactly which CUDA version do you want on, or do we have on this machine. I think we have it. We have 10 on everything, right? Yeah. 10. So you cannot use those for 7.5, 8. So you should be using 10 if you want actually to use that. So something like this. Or you install one of those that are not for CUDA, that they don't include the CUDA. So yeah, which one do you want me to install? This is my module, so I can do whatever I want. This is you can do on your own. You can install them, and after if you don't have not happy, you delete that thing and you create a new one. So don't worry about that. So I will be installing this one, and I will be very, very specific that I want this one and just this one. So conda install this thing, and I just need to put an equal here. An equal sign here, and I will install that one on whatever dependencies that thing has behind that. So you see that it comes with a few other packages, IPython, NumPy here. Yeah, I'm happy with that selection. Yes, go on. Actually, should be fast in my case because I have all these packages on my cache, so it will. I don't know what is downloading exactly that one. So it should be fast, and I get that environment with that version of that. So you can have several. Try not to stack too many packages on the same virtual on the same conda environment, because as soon as you start adding packages, you reach a point where in order to install the new one, you have to downgrade some others. So you start having conflicts, and solving conflicts always result in packages that need to be downgraded. So same thing for people, for example, in genomics, they have a bunch of little packages for doing all sort of things in genomics. Try to install like a subset that makes kind of a well-contained work. And if you need to move to something else, create a new environment and manage that. The idea is to prefer always conda instead of pip. But if some packages, conda covers more than just Python. So you see some of those packages are not Python by any means. So this one is from Intel. This is a trading blocks. This is C code. NKL, this is C code. This is not, those are libraries in C, C++. So conda cover more than just Python. pip is just for Python packages. So if something is in conda, prefer that. Except if you want, instead of pip.
They don't create the same package at the end?
Probably maybe yes, but this is up to the developer. So my package is not even in Conda. I have to download it from pip because my package is just it's pure Python, so it just created there. So it's not that bad. It's and I have my environment there, so I can check on the list, and I will get all the packages that I have installed, from which version, which build, and eventually from which channel they come from. I insert the Intel channel here, so it's trying to pick packages from there if they are available. Otherwise, it will go down into more general channels until it reaches the general one, the base channel. So now, another package that I would like to install is IPython. I forgot to install that one. And you can stack more and more packages. So with IPython, I am happy. With Torch, I'm happy this one doesn't take that.
So Jupyter comes with IPython?
Jupyter doesn't come with IPython. It used to be a part of IPython. They separate the projects because IPython is for Python, and Jupyter generalizes and covers some other languages, R, Julia, some other languages, Ruby. So no, they separate. So you have to search for something. So if you want to install Jupyter, should be around. You can start installing your own packages. So it gives you the control that typically you don't have if you don't know the system administrator when installing scientific packages. That's okay. It's actually much better than rely on the Red Hat packages that are old and yeah, probably very stable, yes, but the old.
So do you think this produces any overhead when you're running the program? Because Red Hat has a kind of binary, and this is on top of Red Hat, so it has to transform from.
No, there is no transformation. No.
So,
what it's doing is basically, Conda is super simple. It's just changing some variables to say, okay, when you need these packages, here is where the libraries are. But everything is executed as a normal Python process, as a normal process in the system. So there is nothing special. It's
not a layer that.
No, it's not a layer that they need like a virtual machine. It's not a virtual machine. It's not something that is interpreting and converting and executing and sending all that. No, there is no mapping or anything like that. It's just redirecting where the binaries are, where the libraries are located, and using that instead of those centrally installed. It's just that. So IPython. Import Torch. And you have actives. Here you can execute this thing as we show you on the Jupyter. This kind of thing works too. Probably will not render very well, but yeah. So it can tell you exactly what it showed the example. So yeah, how you create those things. And you can, this one will tell me, for example, that they don't have CUDA enabled in this case. It was not compiled for CUDA with CUDA support, so I cannot put arrays on that extra device. What else? So yeah. Let me, okay, if I have this working, let me see if I can go into examples and go into NIST and execute this Python. I need a package. Search. Now it's working. Now it's working well. And the CPU version. So this is the example with the NIST, the digits, running as on a script, training the set. I don't know how many epochs it will train, but it's just running. It's just the script. One of the examples in the Torch set of examples, the repository. This thing that I show you here. So here.
But now you are.
And now we are executing this as a script. As a script instead of executing this directly. It's kind of slow because I'm using the CPUs, but yeah, it's working. What I don't know is how many. I think it's 10. So I will take a while on this to train this in the CPU way, but actually I'm not getting that fast. So. It will take a while. Huh? Except for using CPU. So, but I'm the only one doing this. It's using several or just one? All 40. Oh, good. Okay.
So it does parallel.
So yeah, I am doing a bad example here. I am showing a bad example on video because I know you're not supposed to be running this thing on the. So
you use important one CPU without asking anything.
Huh?
So it's doing parallel.
Yes. Yeah. It's using.
Parallel, but you didn't do anything different. Just
oh no! Yeah. This is PyTorch is saying internally is parallelized. It's taking all my cores. It's taking the cores. Well, it's good for you, not so good for the machine. So I will have to kill it. Otherwise, yeah, we'll have to kill it.
You will notice when there is someone using something on their head node, because then everything slows down to no end. It's like, yo, this is not like just to look at something and it will not.
If you ever notice that over that ticket.
Yeah.
And you will receive the famous email from Nate. So every good graduate student receives at some point. You never. Oh.
I haven't. I have emailed him at some point, being like, "Hey, Spruce is going really slow. I think it was." And you were like, "No, it's fine." And then 5 minutes said that you were right. It's going slow.
They were making back in physics. They were making the joke that if you had not received a Nate email about using too much CPU and somewhere, it's because you are not working hard enough in your business.
See, that's the thing. Like, I have it set up already that as soon as I enter, I already have it to like go straight to scratch, so that I don't think I even have anything on my head node. Period. Like nothing at all. Because I know that the moment I start using the head node, it's going to shit, and we're all using too much, so I just go straight to the scratch.
Yeah. What I don't know here is that at least maybe there is one way, but to control how much CPU are you using here, but I don't see anything. I see how many, I can control with this script the number of epochs that I will injecting into this, but still it will use the 40 cores. I'm wondering how to control that. What?
Secret swap, I have to get up.
Yes, yes, but how it from your code, your Python, you control the number of processes. It's just one process creating multi-threading, right?
I'm wondering, could you
Right.
use that process through a PDF script so you can select how many cores you're using during that process?
What?
If you do it through a PDF script where you actually select the number of cores that you're using for that specific process, will that only use those cores that you're asking for?
I'm not sure.
On Thorny, yes.
On Thorny will the way they know it is they will create the 40 threads, but we have some extra protections on Thorny where you get just 8 cores. So those 40 threads will be competing with the 8 threads, and they will slow down your execution, but just your execution.
Yeah.
So I'm trying to figure out if this will work here. And I will put just, let's say,
That's one thing.
yes.
So you're using about half, not even?
No, it's using 2, that's right.
Yeah.
You see this, well, it's using actually
3, right?
like 3, but I don't know why. Because I set up explicitly.
Well, you were using 4,000 before, so
Yeah,
that's definitely improvement.
yeah, it's working, but I'm not sure what it's doing like this.
Hyperthreading is strong in that box, but I don't think that affects that.
No, that should not affect that. Yes. So yes, apparently all that you have to do is just pure OpenMP what they are doing in the CPU version of OpenMP. So yeah, you control it with this variable there, and you get it, and your accuracy is not that bad, 98%. Not that bad. So let me see if I can do something here. Last thing, that's my last experiment here. So this is the GPU node, the GPU cube, sorry. Q sub, we have that. Yeah, I would also know that. What can I ask? 24?
Equals 4. Equals whatever you want.
24.
But you need an equal sign.
Oh, yeah.
Well, if I need to press just 1 because all the measurements.
Just one? Okay. GPUs is plural or singular?
It's
Plural.
What's
Just
the first and second column after the yeses?
here?
Yeah.
Let's see. In Q, right.
So in Q and running, okay.
Here there is just one running. Someone submit something here. Let me see.
I was wondering if when I put Q stat in the GPU merge, it gives me like nothing. But there is 58 running.
It shows by default. He's an admin, so he's installed.
See what?
So it only shows you when you do Q stat in Thorny Flat, it only shows you the ones that you are running on that queue.
Yeah.
I think.
Pretty sure.
Yeah. Okay.
I can turn
Because
that.
that's not the same as in Spruce. In Spruce, you can see all of them.
Okay.
Okay.
I think I can turn that back on if you It's not awful purpose. It's just,
No, it was fine because I was just looking. Because I looked at the JP words and I was like, huh, what does that mean?
you sat mess. Man. You have to have something.
I have something cute.
You don't have internet on this, right?
Yes, but I think that will preserve the data that is already downloaded. So the data is right here in this folder data.
Oh.
They have all those. So I hope they will not try to download this thing again. So that was the thing that screwed me the first time. Python. Let me see. Just in case, Python 3.
It's trying to download.
No,
Oh, no.
there you see. It's a completely different stuff when you run on GPUs.
Very fast.
Yeah, it's another business. And this is rather a small thing, so it's, you cannot compare, but yes, it's so we saw how they behave with GPUs, and this is something that I would really like to show. So yeah, I'm not feeling that. Okay.
Thank you for the work.
Okay.
Very nice.
Thank you. Oh, Gary did all the work. I was just here to thank you, Jeremiah.
Assuming
Okay.
they could have the Jupyter notebooks will be available
Forever. Well,
Okay.
so,
forever. Okay.
hi.
We are working on whatever made here getting more than 3 minutes to breathe to make this actually easier.
Not this.
Not this part, but actually you build each Jupyter
This seems.
or both of you flat.
We would like to offer this kind of functionality
Yeah.
using our class. So you get in, you get something nice for interactive exploration of data.
So right now, if I cannot use that, right? I don't have.
You can use it, but it's tricky.
They're not ours.
Wow.
They're donated to us.
However, I will say that you can, at least with me, I've been able to download most of those as
Yeah, this
PDFs.
is okay.
Like most of the notebooks, you can download them as PDFs.
He'll put all that stuff's in GitHub, though, right?
Yes.
Should be-
So actually, there is something that you can do. So one, you
We
can.
don't get really GitHub stuff.
No, we never get it. So here, if you github.com WUHPC, that's our institution there.
Mhm.
That's what they call it. Here is the repository with all the data, examples, exercises, all the stuff was here, and I will keep it. Probably I will fix the bugs that I found during these days, but it will be there. So that's one thing. Another thing is that if you like to see that, there is something in this one. If you don't, here, you can just copy and paste this thing. The address here. Copy this. Paste it here. But
I think it's looking for a JSON file or something. There's no JSON in that directory. Go back to your GitHub.
yeah.
Is
What I
you
did
go
wrong.
inside one of those?
Yes, but it was working before. Maybe I need to check this. Oh, okay, yeah. So you have to go up to here. So click inside machine learning. You get this one, and you can open the notebook without actually download it, and you can see everything like an HTML file. They have all the figures, all the data. You cannot execute anything. It's just for see only, for read only. But if you want to learn about something, they will have all the exercises, all the figures, all the steps. Or you can download the notebook and play with that. Yeah, so it's the same.
More likely.
And they have nice books here for you. Okay, well, we can touch, right?
Okay, just trying because I know that I didn't use some Python. I script mostly in Bash and TCL. Those are the two that I use the most. Python, depending on what I'm trying to do.
What you can start trying, for example, for your thesis, is if you have, for example, figures that you are preparing for a paper. Those figures could eventually change if you referee say, for example, that you have to change some parameters and you have to recreate a figure. So what you can do is create the notebook that basically execute all the steps to create a figure and export the figure as PDF, the whole thing. And when you have that, if someone in late or the referee asks you to change something, you just tweak that script to create.
So I kind of have something like that because I do my figures in GPU, and I wrote a 400-line script that basically does all the analysis from the trajectories all the way to the graph. And so it goes step by step with the processing.
Yes, Eric. Sorry.
So like the concatenation, sorting, processing. Some of the processing stuff is on Python. So some of the scripts I have, but because I have a mix of TCL, Bash, Python, and God knows what else. So I just basically, I have a script that just basically just press enter and it does everything. All I have to make
Only you know how to do that.
Well, I have to comment it more. I have at the moment where it echoes every single thing that it's doing. So like if it's running, if it's centering, currently centering, it has like echo running centering of trajectories, echo running analysis of script.
Okay, so what you can do, let's say, you have already done working, is to put the Jupyter notebook as a glue code. So you notice that in Jupyter you can do something like this. You can execute any command that you execute in Bash script, like date. Just if you put
because I use Atom for all my writing and scripting. So like I have Atom in both my workstation and my Mac, and I just use Atom for that.
Yeah,
because
that's
it's super easy because you can see all the different colors and everything, and it's really easy to check it out. I've used Jupyter before. It's just for whatever reason. No.
Wait a minute, Nate. Should I stop and
yeah, go ahead, stop.
Stop here and in that case it's not pause. It's just stop.
Stop.
Okay.
You can go ahead.